Welcome back to the DemystifySci podcast, where we explore the very edges of human knowledge. My name is Anastasia.
I'm Michael Shiloh.
And today we have another conversation with John Williamson of the Quicycle Society. We've had 2 conversations with him already, where we've talked about the work of the Quicycle Society, a material interpretation of the mathematics of quantum physics, and today we are searching for the union between the very, very big and the very, very small. This is one of the central cruxes of modern physics, which is that there doesn't appear to be a connecting line between the two. And what really comes out of our conversation is not only some potential explanations for what that line that connects them might be, but also very specific answers to what are the sorts of experiments that we need to do in order to figure this out. How do we create a version of physics that's actually able to engage with these ideas and not accept them whole hog as being true, but as being potentially interesting speculations? How do we reform our perspective of the sciences as being something that is a world of unknown possibility rather than being something where you spend your career just picking at the very, very edge of what has already been done?
And one thing we really want to work towards is a solution to this target fixation that's introduced inside of very well-funded structures, which is to potentially create our own funding structure where we can fund out-of-the-box ideas and fund basic play research that doesn't necessarily have an answer that tacks on to previous knowledge, that might be anomalous and interesting, and finding ways to encourage the excitement about the things that we don't make sense, as opposed to trying to just add extra layers of detail to the things that we already know make sense. So if you want to support that project, check out our Patreon page, patreon.com/demystifysci. All of that money is going into making this an institution beyond a podcast where we can actually contribute to a better version of science in the future. If you don't have any cash to give, that's cool. Just share the podcast with somebody you know, leave a comment, help us understand how we can do a better job here. And all of those little pieces conspire to moving science into a direction where it will actually serve humanity and not just fall into these traps where we're throwing money at something that just eats it and doesn't give us results.
Enjoy the conversation with Dr. Williamson, and we'll see you next time.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
And I think relativity is often explained, or not explained very well. And the way we all learned relativity at university, at least I suppose you guys were the same as I was synchronizing clocks. You had a whole bunch of clocks in different frames and had a look at the relative things you got from space and time from these different clocks. And these clocks were supposed to be synchronized using light beams. And we eventually derived the formula that gamma is 1 over square root of 1 minus v squared over c squared, this famous gamma factor, which is the amount by which rulers and clocks shrink, the Lorentz contraction term. And but I think that's not the best way to look at it. I think the best way to look at it is in terms of the red and blue shift. And if you do that, I've got the place where I did my first calculation of this, and I'm sure I'm not the only one to have done this calculation. But I was just trying to derive things in terms of the red and blue shift because I was looking at wave functions at fully relativistic wave functions for the photon. I was writing a paper about that back in 2016. I presented it in San Diego. So that was the time I was in San Diego conference there on the nature of light, what are photons, and this was one of the 2 papers that I submitted to that conference.
Who hosted that conference? That sounds like our kind of event.
It is, but it is discontinued. It was Chandrasekhar Rochoid Hoorie, Chandra. And which university is that? I think it's University of Pennsylvania. Professor there. I'm not sure, don't quote me on that. Anyway, Chandra's an excellent chap, and there are a couple of co-hosts as well. But he's the guy who had been running that series. But that was the last of them. So they didn't do that anymore. We've been holding events.
The matter had been settled at the conference?
It hadn't. It was just that the funding stream dried up, so it was not possible really to hold it anymore. It's one of those things that's you have to. It had been going for quite a long time, but that was the last of them. Anyway, Martin and I were both there. We both presented 2 papers each. But in one of my papers, I was looking at the Lorentz transformation there, and if you express the Lorentz transformation in terms of the relativistic Doppler shift instead, so you have a look at how much things are blue and red shifted. So the Lorentz transformation becomes a lot simpler to understand. So imagine you have a light clock, which is a perfectly reflecting box with light going backwards and forwards, tick tock in that box. Then, depending on the size of the box, you have a period of that, and you could use it as a clock. Now, imagine a couple of groups of people, one on Earth and one in some spaceship, had such clocks, and that by some wondrous means of super telescopes, they could the people back on Earth could observe the clock on the spaceship and vice versa. Then what would they see? Well, what you'd see is if imagine the spaceship took a huge boost and was boosted up to, let's say, a redshift of 100. So it was moving away from us, and it was redshifted 100-fold. So everything was 100 times longer wavelength coming back to Earth. This is very fast. This is very near the speed of light. So the gamma factor for that is easily worked out if you know what the redshift is. If the redshift is a factor of 100, then the gamma factor is a half of, let the redshift be called R, then gamma is equal to half of R plus 1 over R, where 1 over R is the blue shift of the light. Now imagine that spaceship coming whizzing past the Earth. It's set off from somewhere else, it's come past the Earth. So you're looking at both halves of the light coming in. You can see both the blue shifted part when it's coming towards you and the red shifted part when it moves away from you. So you could measure both. So what you see is that light travels still at the same velocity, the speed of light, 2.997910 to the 8 meters per second, but that it's dramatically shifted in wavelength and in energy. But the gamma factor is just given by 1/2 R plus 1 over R. So for a redshift of 100, 1/2 of R plus 1 over R is, well, it's roughly, well, 1 over R is a 50th, so an R is 50, so it's roughly 50. That's what gamma, and that's a quick way to calculate gamma. And why is that interesting at the moment, and it's topical at the moment, is of course we've had the James Webb telescope come up and give us some beautiful pictures from near the edge of the universe with redshifts, which are utterly enormous as well, and where we're looking at stuff that was only a few 100 million years after the Big Bang. And what they're seeing is they're seeing fully formed galaxies. Now, I'm a big believer in the scientific method, and it would seem to me, if you're looking at something that far back and you're seeing galaxies which are apparently billions of years old, only a few 100 million years after the Big Bang, this is a bit of a difficulty for the Big Bang theory. And that we should really be looking at that very seriously and thinking, is that really what happened? Was there really an enormous starting explosion 13.5 billion years ago? So either there was a Big Bang and it was much further away, or the redshift isn't caused by a Doppler shift, which is another possibility. And there are other theories out there. There's tide light theories, there's gravitational theories where you look at gravitational redshift through concentric spheres. There are lots of other things that could be going on there, but I think this is giving quite a lot of difficulty for the Big Bang model at the moment. And I think that
and there's some other anomalies, right, with redshifts, like quasars that have blue shifted components and red shifted components, and it seems like this monolithic Doppler interpretation requires some sort of nuance to bring it into focus.
I think that's right. I think that we're looking at blue shifts and red shifts and blue shifts. The closest galaxy to us, Andromeda, of course, is blue shifted with respect to us. It's moving towards us. But then there are problems there, because if you look at individual stars there, they've got, if you say that it's just a Doppler shift, some of the stars there have got quite big variations in the blue shift of the of the galaxy as a whole, they really shouldn't be bound to that galaxy. And yet the galaxy is quite compact. Most of the stars are in the galaxy. I think that's a problem too. And as you say, quasars, now they're interesting objects. These things, there's this atlas that Halt and Arp put together as well, cataloguing a bunch of these things, where you seem to have quasars associated with galaxies. They seem to be connected to one another, and they're correlated in the sense that you tend to see quasars quite close to galaxies. You have a whole bunch of these objects. I'm not an expert on this, so I don't know, but it looks to me there as well. The blue shifts of these quasars, the redshifts of these quasars are quite different to the galaxies which they appear to be connected to in many cases. I think there's really quite a lot of work needs to be done there in terms of convincing me, really, in terms of science, in terms of the proper application of the scientific method. It doesn't look to me as though the scientific, as though the observations match the theory that everything is just a redshift.
Well, can we lay out a little bit more the possible alternative explanations for the redshift and how it ties to this interpretation of relativity through red and blue shift?
Well, it's not an interpretation of relativity; it's just a rearrangement of the equations. So what you do is you work out what the Doppler shift is in terms of beta, in terms of V over C, and then rearrange those things. And then just work out what it is in terms of the red and blue shift around the other way around. So you write down, you look at what beta is in terms of what it turns out that relativity does for you is that it allows things and their square root both to have certain kinds of linearity. So you end up with equations that really vastly simplify what beta is. So if we take this factor r, for example, beta turns out to be r squared minus 1 over r squared plus 1. So we're talking there. Now remember that usually you have a 1 over the square root of 1 minus v squared over c, 1 minus beta squared. That's the gamma factor. Relativity turns out it's a hyperbolic curve. And what that does for you is it means that certain objects and their square roots are both linear. And that seems to be a necessary thing in terms of the way that nature organizes itself, by the fact that we do have a speed of light which is constant in vacuum. So, but it's just a reordering of the way you look at these terms to get the r of r plus 1 over r for gamma. And let me see if I can remember what beta is in that as well. Beta again. I've just got the calculator in front of me at the moment.
I mean, the consequence is that either light is losing energy somehow in a non-dispersive fashion, or it's a true Doppler shift and something nonlinear. I don't know. It's hard to come up with the nonlinearity if it's a true Doppler shift. But the explanations that have been given for how light could lose energy non-dispersively, right? Not through scattering, because we'd see different wavelength shifts for different colors. What sort of processes can you imagine that would accomplish that?
Well, I think one of the ones that I've seen is one due to my colleague Robinson. And what he's saying is, imagine the universe was actually infinite. But if we have a photon which is emitted by some sun somewhere, then imagine that. What gravitational pull does it see? Well, initially it has to escape. Let's take our sun. It has to escape from the sun's gravity. So it's redshifted a little bit by the gravitational potential of the sun. But then as it moves out, let's say it moves, if you consider it moving now beyond the galaxy, well, then it has to escape from the galaxy as well. So the galaxy is also exerting a pull on it. Now, if we go to the very, very large scale, so you imagine being such a large scale that galaxies are roughly distributed uniformly in that volume, so you can just consider having a gravitational shell, a spherical shell. Then each subsequent shell, let's say we take a shell which is, let's say, a megaparsec at a time, then each megaparsec contributes the same amount of mass, which can be considered to be concentrated at the center. So then you can you could say if the gravitation could be responsible for the slowing down of the light. That's one thing that I've seen posited. Another one, as you say, there's the tired light idea, that there is some medium, and you're right, it's difficult because you have to find something that would do the thing uniformly for all the different wavelengths. Of course, the hydrogen spectrum simply shifts as a whole as you go further, as you look further and further away. It doesn't. There's no color dependence. There's no energy dependence on the redshift. So there have been various tired light theories proposed. There have been theories proposed that modify Newton's gravitation. That also. I have a favourite one. It's my favourite because I made it up myself once. I don't know if it's any good or not. So and it's experimentally testable. So I thought it might be possible. You see, that light on light, not scattering because light is linear, but light on light might be a possibility. So if you can imagine looking out in some direction in space, you're looking at light coming towards you. What that light sees coming towards you is it sees a sun streaming light towards it. Now, there's a possibility if you have photons coming into one another, then of course if they're high enough energy they can form electron-positron pairs. But at lower energies they can form a precursor to that as well. It's called a twist. It's used in laser physics to help stabilize laser cavities. What you do is you insert a couple of quarter wave plates, and so what you have is you have right circularly polarized light going one direction, and the same circularly polarized light, so also both right or both left, going in the opposite direction. Now these have the property that the pointing vector for the overlap. So what's happening is the two things are rotating in opposite directions. So if you imagine my finger's been, my thumb's been magnetic field, thumb's been magnetic field, electric field, and the finger's been magnetic field. Then this one's going this direction, so it's traveling E cross B. It's going in this direction, and this one's also E cross B, and it's going in that direction. So as the two things overlap, what happens is that the two beams, the electric field and the magnetic field, both add in such a way that they're both in the same direction. And this means that for a case where the beams are overlapping, that the pointing vector E cross B is 0 because E is parallel to B. For that combination.
Is this like a phase decoherence situation?
It's a phase coherence situation.
Coherence. And how does coherence lead to lead to energy loss?
Well, what happens is if the pointing vector is 0, the light effectively stops. So you could also consider that being a virtual electron-positron pair that you've created because it has the same quantum numbers as an electron-positron pair. So if the light stopped briefly, well, that combination has energy and it's stationary. It can, in principle, radiate. So what you then have is you'd have radiation going off, very low energy radiation, maybe 3 Kelvin radiation, so very long wavelength radiation coming off sideways, and the light will be losing energy because of that interaction, because of the slowing down and stopping of light on light. And you could test it because what you do then is you have a look at your redshift. So you look at your redshift over in that direction, and what would matter for that redshift would be a flux of light coming from exactly 180 degrees apart. So you'd look for a correlation between the redshift in a particular direction and the light flux in the opposite direction. And that would be a test of whether or not that was a factor. That would be a possibility. Light on light slowing radiation.
So you're saying that if you look tangentially from the sun versus in line with the radiation that's coming out of the sun, you'd expect to see a slightly different redshift?
You'd expect to see a slightly different redshift if there was if the light was coming in towards a very, very bright source, like a quasar or something like that. So if you could identify or the center of the galaxy in our case, you'd expect the center of the galaxy is quite bright locally. So you'd expect stuff coming from the opposite direction to the center of the galaxy to be more red, to have more redshift due to the very bright object at the center of our galaxy. You'd try for that, have a look and see whether that correlates. Look at the correlation function, see if it's positive or not. So that would be an experimental test of that one.
No, I like that because it's such a simple. It's relatively simple, I think, to figure out if that's the case or not.
I think the thing is that one has to realize that the experimental data is really throwing us something here which says we don't really know what's going on here. And so we really should be investigating a lot more possibilities for the redshift than simply a Doppler shift, I think.
We had a conversation with John Moffat from the Perimeter Institute. And I remember during that conversation, we were asking him about possible alternative explanations for redshift. And we're driving at this question of, well, is anyone studying alternatives? Is anyone that you know of in the physics world looking at possible other reasons that light could be redshifted, except for, the expansion of the universe? And he
or just Doppler
shifting. And he was like, no, why would you look at that? That's not a thing we do.
I think that's a very strange thing to do. I think if you have clear experimental evidence that the Doppler shift is not the only thing for local galaxies, you really should be looking at other things too. So, yeah.
I mean, what I've read is that it's more or less acknowledged that the Doppler linearity doesn't work out for a lot of different reasons, especially with these quasars, but it's explained away in that there's some inherent blue shift component which is dragging the average down in a certain way, and that it's okay. We don't know why they're intrinsically blue shifted, perhaps.
I thought that's because they're moving towards us. There's
parts of the same systems that are inherently blue shifted that then smear the red, so it's not completely linear with distance. I see. But it's certainly an open question. Go ahead.
Yeah, these are objects. Yeah. Why would they be blue shifted? I mean, if the thing's rotating, one half's going to be blue shifted, and the other half's going to be red shifted, right? So it's not a motion anyway.
Well, the quasars are at the center of these galaxies, I guess, is the hypothesis right now. So it's hard that you would be able to refine the part that's moving. If they're just a point source, right? They're supposed to be black holes or something crazy. And so if they're just a point source, how are they rotating anyways? That's a very strange proposition by itself.
Well, that's the same problem with the electron, isn't it? How's that rotating if it's a point?
You said something interesting about the if you have two photons that collide at sufficiently high energy, they create an electron and positron pair.
Yeah.
Can you elaborate on that? Well, yeah, it's the time reverse process
of positronium decay. So if you have spin zero positronium, positronium's like a hydrogen-like atom, but with an electron and a positron instead of an electron and a proton. These things last for quite a long time and then decay into two photons. So, but you can do the reverse process as well. You can have photoproduction of electron-positron pairs. So when I was working at CERN, when you're at CERN, you have a so-called electromagnetic shower, and what comes in is for example, a positron or an electron comes in, very high energy, and then what that does is that photo that produces that generates other electron-positron pairs by collision, but also generates photons. So you have an electromagnetic shower which consists of very high energy photons and very high energy electrons, which decay down through a shower. So you start with one, then you have a couple of photons, and then you have 4, and then you have 8 and 16. The whole thing comes out as an electromagnetic shower. So this sort of thing happens all the time when you're dealing with high energy particles. The things, if they've got an electron coming in with 1,000 times the mass of a proton because it's traveling so fast, will produce a vast electromagnetic shower, in which you have continuously transformations from photons to electron-positron pairs to photons to electron-positron pairs, and so on and so forth. Because the primary produced electron-positron pairs also have very, very high energies, and they can themselves shower and produce more and more particles. You get, it's called an electromagnetic shower. You also get hadronic showers when you come in with a proton, or you hit a proton, or hit a quark, and then you get a shower of particles coming from fragmentation or defragmentation of those particles.
Can I ask you, what is the actual detection? Is it an electron detection? Is it a photodetector? What are the detectors at CERN?
Oh, no,
what is the primary data?
Well, what's the primary data? Well, okay, for example, you have a multi-wire proportional chamber. So what you have is you have a gas chamber, and that's filled with an ionizable gas. And these are, and so, okay. So ionizing particles coming into this chamber, they are put through a magnetic field, so they're bent. And what you do is well, the initial detection is charged particles comes through. That charged particle leaves a trail of ions behind it, an ionized trail behind it. And what you do is you have a bunch of wires, and you put a voltage across the wires. And what that does, if there's an ion in there, the ion will drift. So you have one positive, one negative. So the positive ions drift towards the negative, and the negative to the positive. And you time this. So you time the particles coming through, and depending on how long it takes for the ionized particles to drift to the wire, you know how far from the wire that particle was. So you have a signal coming in which consists of a series of spikes, and you amplify that. So
it's detector voltage that's being measured at the end of the day there, or initially.
Well, what you're doing is you're seeing a signal, which is a series which is potential, which is a current that you get from the multi-wire proportional chamber, which is timed. So you're timing. So you're doing time of flight. So imagine you have two wires just here, and you have a particle that comes through just here. So it ionizes. So you have positive and negative ions. They flow to both their sides. You time how long it takes for them to do that, so you know where between the two wires it was, how close to the two wires it was.
And you're just reconstructing a track, basically.
You're not just, yes, you are, exactly. In fact, the program which we wrote to do that reconstruction in EMC was called Recons for that reason. So you have that point, but then you have a whole series of these multiple wire proportional chambers. So you get a set of points on the path, and you then try and fit that path. And the way you fit it is you use usually a quintic-spline method. So you fit a series of curves to that to try and reconstruct the particles. And what you end up with is a set of particles. You end up with a vertex. You have a vertex which all the stuff flows from, and there's lots of particles coming out of that vertex. And those things are hitting these multi-wire proportional chambers. They're producing hits, which you're measuring. You might get click. You see a voltage spike, and then you amplify that, and then another one coming in, which is a different particle that hit nearby, and then another one further up on a different set of wires. And you use all of that information. So these informations are basically position and time basically position measurements, because the whole thing comes through whoosh, and you've got a whole bunch of particles there. So they're basically position measurements. You then so you get a series of hits which tell you what the positions are in the position is in, if you like, if you imagine Z being the direction of the beam, you have X multi-wire proportional chambers and Y multi-wire proportional chambers. So you have a set of the X and Ys. So you fit those together, and you get a bunch of points. You go, that's a particle track. So fit that. There's one track. This set of hits, that corresponds to another particle track. So we fit that, and that's done like that with gas-filled detectors. But then you also have, for where you're hitting, you have vertex detectors, which might be a semiconductor detector, which is basically a matrix of ionizable cells. So what you then do is the same sort of thing. You detect particle paths in a much smaller detector around the point where you have a target. And in order to start the trigger running, you have a scintillator, which is a fast detector. So the fast detector detects things have come through. You then say, okay, well, this is a hit. We'll read it out. We'll read the apparatus out. The apparatus gives you a series of points, X, Y points, and then the program reconstructs all of those to reconstruct all the particle paths. That's how it works.
Interesting. So you're basically seeing these tracks of ionized gas as they're being formed as a result of some sort of push, crunch, mashing into one another, essentially.
That's right.
The primary readout, yeah. It's very similar to like a cathode ray or something like that, it seems like, the cathode ray tubes.
It is. In a sense, it is. It is, but using the diffusion rate through the gas to give you the time for that, for these things. That works for charged particles. We have uncharged particles as well. You might have a neutrino, which you never see again. So there might be some missing energy, but I could tell you there's a neutrino there. And you also have things, calorimeters. So you surround the whole thing with something that basically just detects energy. And neutral particles coming into that will also themselves form showers, and the showers it'll hit electrons and it'll hit protons within the material, and they will in turn ionize and eventually end up with an amount of energy from that which you can measure as well. So you try and reconstruct an event and then have a look for any missing energy that might be there. That could have been a neutrino, it could be something you actually missed that was missed the apparatus altogether.
So are all of the photonic detections deduced from energy losses, or are there actually photodetectors present? Well, you said something about a scintillator. Is that a radiation-based device?
What a scintillator is what happens is the scintillators are used for primary, tend to be used for primary detection of an event. They're ionizing detectors as well. So you have ionization coming from a scintillator, and then you have a photomultiplier tube. So what happens is the scintillator scintillates, produces light. That goes into the photomultiplier tube, which amplifies that signal if you're using a photomultiplier system, and gives you a readout which is really quite fast. So, but these things are not normally very well spatially resolved. So scintillators are quite big. I'm talking how these things were done in my day in high-G physics. I think they've become more sophisticated since in terms of the way they do these things.
But is the underlying principle that you're detecting the aftermath of something rather than the object itself still the case?
Not really, because the whole event plays out, so its light speed plays out so quickly that what you have is in an experiment where you've got a high luminosity, you've got beams coming in that are producing a lot of events. You have to choose which ones you read out. So you have what's called a trigger. So you have something which you might be interesting. It might be at the ISR where I was involved. The triggers we looked at were things where there was such a hard collision that something came out sideways. So you only look at events where there's something interesting has happened. In fact, early on in the ISR, they didn't look sideways because they thought there would be nothing sideways. They only looked along the beam, and they missed out a whole lot of interesting physics in the beginning because they weren't looking sideways. And then later on, people realized these would be interesting events.
I guess what I'm driving at is that if the detection is so there's a particle that comes in, hits something on the scintillator. The signal that you're measuring is not the particle itself. You're measuring something that happens inside the scintillator. And then when it travels down the path, you're measuring the flight time of the ionized gases, which is still not the object itself. It's what it's done to the gas that it's passed through.
Okay, the reason you know what the different particles are is what you have a three-dimensional view of all of these particles. And what you do is you know what the mass of the particles is because you measure their charge to mass ratio by how much they bend. Now, you know that the charges are going to be +1 or -1 pretty much. So you're measuring masses of the particles by having a look at how much they bend. You're measuring the momentum of the particles by that. So you're having a look at these, and because different kinds of particles interact in different ways, you have different profiles. You have a different profile for an electron, or for a hadron, for a proton, for a sigma particle. You know that a lot of the particles are, because you see them being produced and they fly for a little distance and then they decay because a lot of stuff decays down into other things. And then you measure what those other things are. And then by reconstructing what comes out of a particle, you know that you had a particular hadron by its decay products.
But the path, as the path curves, again, what you're measuring is still this ionized trail that it leaves behind.
I think it's worth trying to. I think you have to pick apart what is meant by the word particle here.
That's what I'm trying to get at.
Because the word particle here seems to mean events.
Well, right. I mean, like, there's the
detection events.
I think that this is the difficulty of the word particle. I think you're exactly right, because it's easy to consider it as, this little bowling ball that's flying through space that's doing something as it goes. But what's really being looked at is a trail of
causality.
Of causality, yeah. I think that's a good way of looking at it.
Right. I mean, at the bare minimum we could say is that one gas atom is doing something to the next gas atom that's doing something to the next. And we call these events, this transduction of momentum across the ionized gas, a particle.
The particle path.
A particle path, yeah.
Well, what you're also doing is you're putting amplification into it. Because you have an electric field, what happens is one ionization event the stuff from that will accelerate, or can be made to accelerate, to produce more of them, which produce an amplification effect. But what you're analyzing, of course, is you're not analyzing the little trails themselves. What you're analyzing is the reconstruction that you've made of what these particles are. So for a particular pi plus path, which lasts for a little while, so it'll travel a little way and then it will decay off into a muon and an electron. What you're analyzing there are very many of these points, not just one. Mm-hmm. So it's not a single event that you have. You have a whole series of them. So you see you see the curve of the thing moving along, and actually when the primary particles are moving very quickly, so they're almost straight lines. They have a little bit of curvature. That little bit of curvature tells you they have a very high momentum, and then you work out what they were according to what they do, how long they last, how they decay, what their masses were. You get it from the particle kinematics.
I mean, it strikes me that the shift... So, I mean, if you were to ask someone who works at CERN what the particle is that's coming in, would it be described through quantum field equations, and that would be the end of the story?
No. It would just be charge and mass. It'll charge and mass and lifetime. Those are the things that you're not using quantum stuff at all. You're talking about little balls.
Just simple Lenz's law kind of thing. Charge and magnetic field drifting.
So the next question is there ever a conversation about what is charge? Like, do people at CERN sit around and ask that question?
Yeah. Well, no, not really, because there are those conversations, because I was there and I'd be having that conversation. But that's not the kind of question that people are asking. People are taking a set of things as being given, and those things that are given aren't. Charge is absolutely given, plus or minus 1 or 0. That it's only there in terms of the bookkeeping of charge. That charge is absolutely conserved, and it comes in unit quantities. Except when you're looking inside hadrons and you're trying to look at the charge of the quark, which has not really been done successfully, to my knowledge anyway, yet. There's been no evidence for charges other than unit charges. There have been some papers claiming to do that, but they've all fallen by the wayside over time, as far as I know, at least. I haven't followed the field.
Do you have a hypothesis, or do you have a definition for charge, or do you have like a material representation of the idea that you've stumbled across in the years? Yes.
Stumbled across it? No, I wrote a paper about it.
All right.
No, so my 97 paper was saying what charge was, what charge is, and what charge is it's so what is charge? Charge is, for me, charge is rectified electromagnetic field. But what you have in a photon is the thing is going round and round. So for everything that's going leftwards, you've got an equal thing going rightwards, averages to 0. But if you take that twist of the photon, so the basic idea is this. You have light, which is represented by, imagine the electric field is down on the black side and is up on the brown side.
He's holding a belt here, if you're listening.
Well, this is a belt just here. Now, what I'm going to do is I'm going to put a single, it's a bit of a long belt, actually. I'm going to put a single twist in that belt. So I'm going to twist it around by 300. It's not a Mobius strip I'm going to make. I'm twisting it by 360 degrees. And then form the thing, make the thing by some means, and that means comes in my later theory, my 2014 theory, so that the stuff comes back and it bites its own tail. So I've just made that thing here. So here's a belt. Now this belt has some tension in it because it's torsion in it, because it has a twist in it. But what it forms something where the electric field, remember the electric field was down into the belt. So now the electric field is down here and it's down all the way around. Now where does electric field come from? It comes from light being trapped. It comes from the light that was originally. So I'm taking light and I'm making the light twist around and bite its own tail. Now that was the subject of my 1997 paper, which was basically what if you take light and for some reason it confines itself, and instead of traveling in a straight line, it goes round and bites and round in circles. So if you do that and you put in the energy of the quantum, E is h nu, and use Gauss's law to calculate what the electric field is pricking out from this, or pricking in from this thing. We have the field going inwards. This is an electron-like loop. So look, it goes. So whereas before the electric field was in all directions and was just periodic, now it's always radial. It's always outward directed, or inward directed in this case. So it's always inward directed all the way around the loop. So anywhere from my fist, you see that the black side of the belt is everywhere on the outside, and the brown side's on the inside of the belt. So what you've done is you've taken something and you've made, in radial terms, the thing rectified so that it has a DC, it has an electric field which is pointing always outwards. You take something which is uncharged and produce a loop. And of course, these loops aren't produced by themselves. You can't just make light do that because it doesn't conserve angular momentum, doesn't conserve spin, for one thing. You always produce one like this, but you also produce equivalently let's just see if we can make it happen. So I'll just take the same loop and try and get I'm not getting the brown on the outside, but you can produce the same thing with the brown loop on the outside. Let me just see if I can do that. There we are, that's the twisted strip now with the brown side on the outside. So that would be a positron, and these things are produced in pairs. So you get electron-positron pair created. So if you do that, you can then calculate what the charge is from the spin, because the spin is h bar of a single photon. So and we know that E is h nu. So we know how much electric field there is. We know how big this thing is because it's a single wavelength that I've put here, a single twist. So we know how big this radius is. That radius is whatever the length of the belt is divided by 4 pi. It's a double loop. It's a fermion and an electron. So lambda c over 4 pi gives you the size of this thing. And it works for any energy of any photon. So the mass of the electron is something that comes from somewhere else. I believe it comes from the interaction with the rest of the universe. But anyway, if I take this thing at any energy and calculate its charge from E as h nu for that photon, then what I get is I get the charge of the electron within a few percent. So what the electron, so what you're doing is you take an uncharged object, something which is spinning around and round in all directions, and you're forming it into a loop so that in such a way that the electric field is now radially directed. So it's pricking out like a hedgehog in all directions, and that's a charged object. And you produce these charged objects in pairs, and that's what charge is for me. Charge is derivative of angular momentum.
And so
derivative.
What is the impulse that you have to apply to get it to twist around like that? You said that it doesn't do it on its own.
We didn't consider that in the 97 paper. We just said, what if it did that? Then what would the properties of that thing be? But this is now 2023, and I can give an answer to that question. The thing is that what you have is a set of field equations. I wonder, this is a little bit hard to do in a podcast, of course. But what you need to do is get a proper theory of electromagnetism which allows solutions which are going round and round in circles like this Now, Maxwell's equations do not have such solutions. So it's pretty easy to show. In fact, one of the Maxwell's equations is exactly that. It's the divergence V in the absence of a charge is equal to 0. So div is 0 precludes a charge. Now, so what I did is I've written a set of other equations, and the equation can be stated quite simply, but appearances can be deceptive. What I did is developed a series of equations which are the four derivative of this of an extent of this Ur stuff acting over a scalar, a vector, a bivector, a trivector, and a quadrivector system. So a system where you have light and where the bivector parts are electric and magnetic field, and the scalar and pseudoscalar parts are a kind of a complex mass field. Now, it turns out when you write those equations down and look at the forces that you get from that, you look at the forces by looking not at D. Okay, so the extended equations, the extended Maxwell's equations written in 4 vector notation are D of F equals 0. These are the free space Maxwell's equations, where F is the 6-component bivector field, 3 components of electric field and 3 components of magnetic field, be written in a bivector equation. That's Maxwell's equations. That's the field equation. 4 derivative of the 6 components of the field give you 24 components, and those 24 components fall into exactly all 4 Maxwell's equations. So that's dF equals 0. If instead of just taking F, the 6 components of the bivector, you take the other components, the vector components, the trivector components, and the mass components, you get a more complex equation. It has 64 terms, 4 times 16 terms. 4 differential of a 16-component object gives you 64 terms. Now that has components, which mean that if you now look at the pointing vector for the system, pointing vector in electromagnetism is given by E cross B, the vector product of electric and magnetic field. So if you have an electric field perpendicular to a magnetic field, the momentum is E cross B is a vector which is perpendicular to both, the cross product of both. That's conventional electromagnetism. In the full equation, in the Williamson-van der Mark equation, there's an extra term in that equation which is perpendicular to that. And that extra term is PE. It's the pivot of mass term times the electric field. Now, what that means is it means that if you look at this belt, and I look at an element of the belt, then really transport is E cross B along the belt. But in the presence of pivot, there's also a term which is confining, which is down in this direction. So the momentum is curving in the full equations, in the full relativistic equations. Now, those full relativistic equations are actually an extension of the Dirac equation. They're relativistic quantum mechanics equations. So in the new relativistic quantum mechanics, the thing goes round and round in circles if P and B have the same magnitude. In other words, if the mass term expressed in root energy terms has the same magnitude as the magnetic field term. So you end up with a 4-component wave function, which confines, which is an electromass magnetic equation. That electromass magnetic equation has solutions which go round and round in circles, which do this double loop.
So what I'm hearing you say is that the particular twisting motions of the Ur stuff, whatever it is that's moving, is different for a charged body like an electron system, like an atom with an electron, versus light, which has a different shape to it. And in light...
Very, very close. What you're saying is very, very close to correct, but not quite.
Okay.
What's happening is, it's not the fact that it's charged, it's the fact that it has mass that's important. And the mass makes it go round and round in circles, and the fact that it goes round and round in circles gives you the charge. So it's not that the charge is doing this, the charge is a result of this. It's not the cause of this. The cause is the mass.
I thought one thing that you said I wanted to draw attention to that I thought was really interesting. You talked about how this sort of angular momentum in light has a torsional quality to it. And I was trying to, everybody teaches light is a transverse wave. And the other day I just started Googling around for where in nature do you see transverse waves? And the only physical representation of transverse waves I could find is twisting on something so that essentially the shear wave is perpendicular. So essentially twisting on an object. It's a torsional deformation. That's really the only physical representation of a transverse wave that's possible.
Well, you get transverse waves from an aerial when you just have an aerial sticking and you and you put current up and down it. That produces a transverse electromagnetic wave. So that will give you a transverse wave.
Right. But in terms of anything other than light, what in the world would produce transverse waves?
You mean like a macro scale object?
Yeah. What in our everyday lives? Where in the world would you ever see a transverse wave? And there's only one place, and that's twisting on an object, essentially.
Yeah, I see what you're saying. I think much more usual are circular waves. If you throw a stone into a pond, you get circular waves.
Yeah, at interfaces you could see something like that, but in terms of occurring within a material, where would you see that other than at an interface? It would be by applying a torsional deformation to some object, essentially.
I think we might be talking a little bit at cross purposes, Michael, at the moment. Are we talking about transverse waves as in E and B are perpendicular to the pointing vector? Are we talking about transverse waves as in terms of linearly polarized waves?
I don't know. I don't totally understand. I guess I was talking about linearly polarized. Yeah, well, circularly polarized waves.
As opposed to circularly polarized, yes.
So hold on. Linearly polarized is a mixture of left and right polarization. Circular polarization is directional polarization.
L plus R, yes. Yes.
I remember being really frustrated by that being the case, that a linearly polarized light is not unidirectional. That seemed frustrating.
Well, there's a whole polarization. You could have elliptically polarized light as well. You can have stuff that's in between linear and circular. But the thing about circularly polarized is that these are the eigenfunctions of angular momentum for the light. So if you want something which is properly plus or minus h bar, then it's right and left circularly polarized.
I think that what what Shiloh's really driving at here is that in the model that we've been working on, there are these filamentary connections between atoms. And so I always talk about this in context of so let's start with a single atom universe. In a single atom universe...
Well, you need two, at least.
Well, is there light in a single atom universe?
Yeah.
Is there?
Sorry? What did you ask?
I said...
You broke up for a second.
Is there light in a single atom universe?
No.
Okay. So
because you need to have an emission and absorption.
Perfect. Okay. So then if you have a two-atom universe and you have this filamentary connection between the two atoms.
We have some Ur stuff
in between the Ur stuff is between them. So it radiates, let's say it radiates outward in all directions, but light can only occur in the Ur stuff that lies between the two atoms.
Yes.
And so and we know that the atoms are moving, breathing, pulsing, whatever it is that they do. And if you excite one of the atoms so that it is in a different vibrational mode than the other one, what you'll have is a tension, a torsional wave that travels through the filament to the other atom. And that packet of torsional deformation is in our model of the photon.
Yes, that sounds pretty good to me. So what you have is so imagine something which goes from a 1p to a 1s orbital, so it gives 1 unit of angular momentum, and we have an h-bar photon which is transmitted from the 1, and it goes linear in a line between the emitter and the absorber. Okay, pretty much. So like a filament, exactly. And what it's doing is it's transferring 1 quantum of energy. So 1p goes to 1s in the first atom, and if the other atom is identical, then it has a 1s electron which gets promoted to 1p. Click, and energy is nicely conserved in the whole system.
And so what Shiloh's driving at is that when you were taking the belt and you were twisting it to get the standing transverse wave in it, that's the propagation the propagation of that circular polarization would be in this model, the photon. And I think that that's, and so what he's basically saying is that if you go into the macro scale and you look out onto the world, it makes sense that that's what the micro scale structure would look like. Because the only way that you can get that shape on a large scale that you can actually see and touch is by taking an object that is, say, flat and then twisting it and then getting the helix in it, so to speak.
I like the way you think. You know, a lot of people are thinking about these things as a transactional thing, that you lose a unit of angular momentum here and that you have a transmission of a photon, which then gives a unit of angular momentum. You're thinking in terms of numbers, in terms of quanta. You're not. You're thinking in terms of structure. You're thinking in terms of the way this... And I think that's what we need to... That's where we need to go next. We can't just keep thinking. It's brute force ignorance to think that you can't get inside and understand how elementary particles and atoms work. We have to do this.
Well,
this is the next thing.
I mean, when I was in grad school, I worked almost exclusively with the atomic, with the atomic force microscope, and we had our lab. Actually, my PI at the time developed a really special kind of atomic force microscope where the cantilever. So just to like fill everybody in, atomic force microscopes work by essentially vibrating a cantilever that you deflect a laser off the top of, and you can get great topology off the surfaces. You can get even single atom resolution this way. But what Oscar did, my advisor in grad school, is he developed a kind of AFM that not only vibrated in the Z-plane, but it actually wobbled, right? So you get a torsional readout. So a lot of the math that we were dealing with was torsional, and it occurred to me that the math associated with the transverse waves in photonics was completely commensurate with the torsional vibrational harmonics of the cantilever system that we were working. Like exact same quantitative relationships in terms of torsion and transverse waves. And so it's kind of like the only option that's left on the table at the end of the day, if you want a material representation of what's happening during light, is that something is being helically deformed, because mathematically it's identical.
Yeah, I mean the maths of circular polarization is of a helical wave moving through space. So yeah, no, exactly, yes, right. Yeah,
And-
same maths.
And so the next, I think that the reason that this is conceptually unpopular or difficult for people is because the next thing that once you say, okay, so there is this, there has to be an exchange of information between the atoms. If they're not momentum, and so they have to be connected to one another. And then you have this object that's changing shape. The object has to have subunits, and then you have to start thinking about, well, what are those subunits? What does it mean for something to have subunits on a subatomic level, and how does that look, and how does that work? And it's hard to talk. Go ahead.
Yeah, you're making life difficult for yourself though by saying, you see, I think where people make life difficult for themselves, they start by telling themselves a story. And then the initial story is then the thing that produces the difficulties. But what you're saying is it has to have subunits if it's transmitting energy. But energy is something which is kind of something which doesn't have, well, it has units, but it doesn't have. It's a fluid which for photons can go from 0 to infinity in terms of an energy. It doesn't have subunits in that sense. It's a continuous thing.
I think she's not saying that the energy has sub. She's saying that the Ur stuff, in order to deform, must have subunits. Essentially, there's no way to deform an object that doesn't have substructure. Essentially, and so when
you're saying deforming, you're saying that we're thinking about some sort of space, right?
We're thinking about an object. So if the belt, when it's flat, is just the lowest energy conformation for the connection between these two atoms, as you start to exchange momentum between them, it's the belt that has some kind of...
It has to change shape, which requires subunits, essentially.
I think that's the basis.
Well, you say it requires subunits, but I don't get why it requires subunits.
Well, I mean, if I had a perfect solid with no subunits, there would be no way to deform it, because there would be no way for it to change shape. In order to change shape, you have to have articulations in order to do it.
Yeah, but I see what you're saying now. The thing is, that thing has to change shape with respect to something. So you have to have a framework within it which it changes shape. What if the essence is the shape? So you have a form, and that form that form is the particle. So in my model here, the form which represents electron is this double loop.
Yes.
So that shape is the particle. The shape is the thing.
Which gets back to what a particle is, right? Which is this whole convergence of attributes.
Yes.
Well, hold on. The double loop is a shape that emerges from the flat photon path, right? So there is, in order to create it, there is a shape change relative to the state that it is in to begin with.
There's certainly a topology. That's
and
right. Yes.
So as that topology, as if the topology of the object is changing, then that is a shape change of the organization of the material inside of the object, right?
Because this thing that we're calling a particle is dynamic to begin with, right? It's already something in motion because it has momentum to it.
That's right, but what we're saying is the substance here is the dynamics. So the substance is something which looks like a differential. So energy. Remember, we were talking last time about energy being frequency. So it's the dynamics which contains the energy of the object. So you could imagine that we were sitting in a matrix which had a random. Perhaps it has properties that are defined by epsilon and mu, perhaps. But if we're talking about the fabric of space-time, we're not looking at the fabric of space-time. We're looking at deformations of the fabric of space-time as being particles. Mm-hmm. We're looking at deviations from the flatness, which are gravitation, and so on and so forth. So it's not the thing itself, but it's the change of the thing which we're looking at, the dynamics of the thing.
Exactly, so but that necessarily implies that something below that is in motion. I mean, if your theory starts with something in motion, there has to be something that's fundamental to that.
But why can't that thing be something which has an energy density, but is in fact smooth? It doesn't necessarily have to be particles, like light.
Well, light, right. So
does it help to define energy at this point?
Yeah, probably. I mean, it's hard to make a definition for energy other than some stuff in motion of some sort. You could obviously have potential to go into motion, but energy is a dynamic concept. It implies that something is moving. And so what that something is the question that we started out with. Is that
let's drill down into this stuff thing. What could the fundamental stuff be? Now, I don't think it can be a set of particles. I think it has to be an amount of formless fluid. Really, it's the form that gives the particle.
But fluids are articulated by subunits necessarily, right? That's what gives them all of their incredible properties.
That gives them the ability to flow.
Well, that's not true for light, though, is it? What's the subunit of electric and magnetic field? What's the particle of electric and magnetic field?
Well, the electric and magnetic field represent the motions of the subunits as they deform, essentially.
Because if you have a radial architecture for the universe, if all atoms are radiating outwards,
their structure, their physical structure
is radial, then the electrical and magnetic properties have to do with the architecture as it moves.
It does, but remember that what an interaction is. It's a transaction between such objects. So something is transferred. Now, what is transferred? Now, what's transferred I'm sitting in a lovely warm room, and what's being transferred to me is the vibrations all around me of 300 Kelvin roughly temperature. But what's being transferred it's not just 300 Kelvin photons that are hitting me. It's we've obviously got the 1,500 Kelvin photons here, and I've got a halogen light up there which is giving me some 3,000 Kelvin photons. So what's happening is that and also at 300 Kelvin there's a vast spread Poisson spread from absolute zero to quite high energies, I'm getting packets of energy coming in of all values. And those things are not divided into subunits. The energy is continuous.
The energy, you're feeling the pressure you're feeling an event, right? You're feeling the momentum being transferred to you. But the momentum is being transferred through the ore stuff, which is deforming, and that's how you're receiving the momentum, essentially.
Well, that's right. But what I'm getting is I'm getting a transaction. I'm getting a packet of energy from there to me, or I'm putting out packets of energy from me to the stuff around me, which is warming that up.
Mm-hmm.
So, but that packet of energy could have any value from 0 to, well, as large as you like, or as large as is feasible. So,
that's right. Yeah.
Continuous. That's not divided into units. It's not.
Not the energy. Yeah. The problem is look, all words represent either ideas or bodies. You could have abstractions of both, but we're talking about energy as an idea. It's an amount of push that you're receiving, and that, of course, depends on all sorts of non-discrete factors. But ultimately, the stuff itself that's being deformed is discrete. Even though it's completely hypothetical, it must be discrete because it's a static concept. Bodies are just static concepts. They can move around, but the push that they feel is an idea. The energy is an idea. It's not actually a thing that has a structure and so forth.
Like the radial network that is in the room that all of us are sitting in, right? So
the worst stuff.
There's obviously void in between you and the object in front of you, because it's filled with gas, but there's also these filamentary connections that are between you and the gas molecules and you and the light bulb filament. And
photon exchange, yes.
Exactly. And so when we're talking about exchange of temperatures, you're exactly right that each one of the molecules in the room has some energy with which it's moving, and when it hits you, it transmits that energy to you in terms of temperature, right?
Mm-hmm.
And so if you have a network of filamentary connections, each one of those filamentary connections can take whatever energy state is being put into it by the atom on the other end. It's just that there must be these discrete paths of travel between the atoms themselves.
I think I see what you're getting at. There are discrete paths. The amount of stuff that can be transferred is arbitrary, but the ends aren't arbitrary, and the ends are particulate. They're not just particulate. They're systems. They have to be systems. A single electron can't radiate. You need to have some collective excitation, where you need to have some atom, or you need to have some molecule, or some solid to start being incandescent and radiating. So, but the stuff that's transmitted is transmitted through a medium, and that medium can be any energy. Mm-hmm. So, but I think we agree that the actual particle thing is it's a topology, it's a shape, and those topologies can interact. And things that don't have the property of having a center, I think we might be about to agree, at least to a part. I think it's absolutely right that you can't have, in order for something to be able to interact, it has to have a center. It has to have a place which is going to which it is interacted to, or from which it can interact on something. That thing has to have like a bookend. It has to have a place. It has to have I'm using place instead of position, because position is an extensive thing, and I'm thinking about a thing which is self-defining at a point around itself.
What about surface?
Well, yes, that thing is really something which is rotating, and which is rotating to form a spherical object. It has a surface. It has an interior and an exterior, and a surface. And if I'm trying to interact with that, then it's a pretty high energy thing. But if I'm trying to interact with that, it'll be embedded in some system in a hydrogen atom, which also has some form like this. But the form in the hydrogen atom the proton is much more complicated, having a more complicated path, as I talked about in the first talk I gave. That object has an interior and an exterior. And if I'm trying to come in with a photon onto the interior of this thing, I'm going to have to deal with the surface of that thing. It has a surface.
Mm-hmm.
And it has an inside and outside. Now, that surface means that in the vicinity of this object, space-time is not as smooth as it was had the object not been there.
Mm.
Finds a region of space-time which is just not accessible to a class of objects, that class of objects being other photons. So anything coming within that, well, at least 1/137 of the time, will not be able to access that interior. And that means a bit of the space is effectively missing, and there's a surface to that space which is protecting the interior of it, in my view. But I think that's quite similar to what you're thinking of. You're thinking about electrons having a surface as well.
Well, we'll be very, very careful to not call electrons bodies, first of all, because they're a dynamic concept. An electron has motion inherent in it, and so
it's an apparent surface.
Well, sure, but we start with the assumption that something is moving to produce the surface that we call the electron shell of the atom or something like that. And so we just have to be very careful to recognize that particle is a dynamic concept. It's something in motion. But stuff units, which I like to call fibers, the fibers that are actually the medium responsible for this motion, that's a static concept. That's not in motion to begin with. It's in motion to produce the electron, essentially. Does that make sense?
I think that whatever that worst stuff is, it must be conserved. Because we're talking about something which, when you square it, has an energy density. Now, it can take many different forms. And we know that energy can take the form of being, it could be a frequency, it could be a field density. Field density also has an energy density associated with it. It could be the effective mass of a local particle. That's also an energy. So 3 different kinds of things, at least, that it could be. So
that you could measure it with, essentially. That would be readouts of its energy or its motion.
Yes, at least one could imagine it to be so. Perhaps to actually measure it is a difficult thing, because even when you're dealing with the atomic force microscopes or with my particle collisions, the trouble is that you're kind of limited by having a piece of material, or at the very least a single electron or something, or a photon with which to do your probing.
Yeah, so inherently you end up with hypotheses at some point, because you can't actually look, since atoms themselves are made out of the ore stuff and the connections between them are made out of the ore stuff, there's no hope of actually being able to probe the shape of the fiber of the ore stuff. You have to deduce the concepts hypothetically based on the interactions you can observe, which turn out to be dynamic, like electrons, protons, things like this. And so you're necessarily in the dark when it comes to the shape and the architecture of the ore stuff.
I think what we need to do is get to the stage where, we need to look at experiment, and we need to find things that are consistent with the experiment. At some point, we're not going to be able to say exactly what that stuff. We may be able to isolate it. There's a possible experiment I proposed a few years ago, which would be interesting to try. I should say that I don't think this will work, but it is a thought. It is a thought. What you could do is try and produce, not your stuff itself, but you could try and produce just free scalar mass without the field. And the way to do, I think the way that one might be able to do that is by cancelling fields. See, the thing is, imagine you have an electric field. Electric field density is half epsilon E squared, the energy density in that electric field. Now, let's imagine you cancel that with an equal and opposite electric field. You have some energy density in this, you have some energy density in this, you cancel them, you get 0 electric field. Where has the energy gone that was in those 2 fields? Because fields add linearly. Now, in a static field, you can say, okay, well, what's happened is the field cancellation has occurred at the sources. That one's cancelling the potentials. So But if you have a situation where things are moving rapidly, so that the sources have moved away by the time you do the cancellation, so you have some field coming in from somewhere, some other field coming in from somewhere else, sources move away because they're moving extremely quickly or they're hit by something else, then there's a possibility that one could cancel field. If it does cancel, what would it cancel to? So an experiment will consist of trying to put a field configuration in place. And the first field configuration you try would be the twisted mode thing I talked about, where you bring light in and the light slows down or is stopped in this region where the overlap of the two, of the left going and right going, right circularly polarized photons happens. If you can produce scalar stuff from that, the only force it would feel would be gravitational. So if you had a laser and you came in with left and right circularly polarized light, stopped it, you might find something falling down from that which has mass but no charge, and you might be able to measure that by probing it perhaps with a third laser underneath the first two you started with. So it would be fun to try and do that. I don't think it would work.
That's very interesting. Yeah, the way that I hear that is that if you put the right energy into these connections between atoms from each side, you momentarily lessen the tension on the system, essentially, which would be felt as a gravitational effect, where gravity is the aggregate tension of these atoms upon one another.
So you're saying that you'd feel less gravity?
Yeah, either less or more. I'm not sure how the photon's constructed. More, yeah. So you add tension to the system. That's where the energy goes.
Difficult to measure, of course, because it's an only small amount of gravity. You need to measure it in some other way. Might be difficult. Anyway, can we take a short break?
I kind of wanted to get back to the cosmology side of things, because I feel like we brushed over some very important possibilities here. One, you mentioned that if, in fact, this distance redshift relationship is not exclusively Doppler, then either our conception of this bang is off, or perhaps there was no bang at all, in which case the extreme possibility is that we're in an eternal universe.
Well, I think that...
Yeah, go. I'm just curious why people... All right, so for me personally, it seems like by default, you have an eternal universe, and then it's on you to make up some kind of mechanism for how it's not eternal, which is, I guess, what the Big Bang is trying to do. But it seems strange to me that people have such a hard time with even considering this possibility of eternity because it's not congruent with their own lives or something. I don't know. Why do you think people are so, scared of this idea?
I don't... I'm not entirely sure, but I think that what's happened is, I think the trouble is when you get a big idea, like a big bang, that it tends to have a life of its own. We're talking about stuff that was developed back in the 1930s, so nearly 100 years ago. So there's a whole culture that's built up about this idea. I think it's hard to shift that. I think it's just hard to shift something, and it's also such a good creation myth, isn't it? This idea that everything started in some enormous explosion. But coming back to the possibility of an eternal universe, there's one fact or near fact that struck me at one stage that I got from Feynman, and it wasn't Feynman's idea in the first instance, but and that is that the idea that the total energy of the universe we live in is just is zero. We're living in a zero energy universe, and the basic. Have you met this idea before?
Mm-mm.
Maybe not exactly. Just that all of the different displacements would add up to zero at some point. Essentially, like all the push and pull would cancel out at some point.
Yeah, I mean, it's that kind of... I mean, the basic idea is that you have a universe, which is whatever it is, 13.5 billion light years across, and it contains quite a lot of mass, about 10 to the 80 odd protons worth of mass. And that's quite a lot of equals mc squared energy. That's pretty huge energy. So it's a very large positive energy. However, you also have each of those particles in the universe is attracted to every other particle. So each one of those 10 to the 80 particles is attracted to all the other particles. And that mutual interaction is a negative potential energy. But there are a very, very large number of those interactions, because for each particle you have an interaction with every other particle in the universe. So if you integrate that up, you find a very, very large potential energy, negative potential energy, which for estimates of the size of the universe, the number of atoms in the universe, turns out to be almost equal and opposite to the positive energy from E equals mc squared. So then the total energy of the universe, if this was the case, would be mc squared energy minus the potential energy of all the gravitational interactions, which would sum up to absolutely nothing at all, that everything is nothing and nothing is everything. And the entire universe had zero energy. Now, that struck me as being an utterly wonderful idea, that the entire universe could simply be a reordering into a more likely form of absolutely nothing at all. And if that was the case, then one has to try and look to theories that tell you how new material could come into being. But I think that if we're looking at interactions, and we're looking at interactions which take place at the same point in space-time, one has a possible way of looking at the way that things might come into being in the very, very beginning, that what you need to do is to go to a situation where thermal fluctuations can produce new matter. Now, at the moment, we're such a long way, because even the lightest stable particle, the electron, has 511 keV of energy. It's a very massive particle. But anyway, if you're producing it in terms of electrons and positrons, which annihilate with one another to give you energy once again. So that doesn't seem a very fruitful route. However, if one imagined a universe where there were only a few particles, then, or if you imagine a universe which is where the particles are very, very much larger than the present day particles. Now, why do I think that might be a possibility? I think it might be a possibility because of the discussion we're having the other week about the way that gravity works, the way that you're adding energy to your body when you climb a hill. You're winding up the particles in your body, and essentially, as you go down into a gravitational well, everything slows down and everything gets bigger. So the bigger the gravitational well, the bigger everything gets. So if you start thinking about going to things that are really very, very close to being black holes, you end up with particles which are very, very much larger. And at that point, one might have the possibility of having fluctuations actually creating matter. Now, there's a movement which was started, which looks at gravitational equations. And I'm not the right person to talk to about this. I just know of this movement. I'm not an expert on this at all. But which posits that black holes are really not a proper solution of. I'm trying to remember the name of the chap who introduced me to this. Crothers?
Steve Crothers, yeah, we've had him on the show.
Yeah, we know
you've had
Steve.
him on the show.
Yeah, he's a good friend. Yeah.
I'm delighted. Yeah, he's a great guy actually, because I read his paper. He had real trouble, as you know, with getting his stuff out, and got thrown out of his PhD and things like that. As far as I understand, absolutely scandalous behaviour by the university there. But I think he's spot on the money in terms of saying that the solutions which are being done for black holes, the sort of Schwarzschild solution, are just not proper general relativity, because they're mixed solutions. And when you do it properly, you don't get down to a black hole. What happens is, in some sense, the universe is a black hole because light doesn't get out of it. So, and in fact, the equations for that are the same as the equations for a black hole. But in that case, as you go into a very, very big gravitational potential well, particles get bigger and bigger until eventually, I think you might be able to thermalize the creation of particles. Now,
and by bigness, you mean more massive?
I mean less massive.
Oh, less massive. I see.
Yeah, because that's what's happening. Is you go into
What do you mean by bigger? Sorry, do you mean occupying a greater volume? What do you mean by big?
Yes. Yeah. Yeah. I mean, big is small and small is large. So big size is small energy.
Can you define mass?
Can you define mass? Well, equals mc squared.
Okay.
Oh, bless you.
Thank you. Okay, so if you dig deeper into this, the thermalization and the creation of mass, then.
Well, I'm just wondering how particles could be created, and this goes into my idea of three lefts equals a right. That what you have with the electron is you have this double loop, you have this object. With a proton, what you have is something which is looping around, going nearly around through 720 degrees, but then coming out at right angles, and that's then going around another loop perpendicular to that, which is going around another loop perpendicular to both of those. So you have three perpendicular rotations, which of course you can have in three space. So, which lead to a complete particle, and that's the idea of what a proton is. Now, if that's the case, it means that the sense in which the electron is going around, the difference between an electron and a positron is electron has the mass components are always positive, mass is always positive, but the root mass components for the electron and the positron have opposite sign. So one's plus and the other one's minus. So, but in the case of protons, because you're going round, you're essentially round a three-quarter turn. And a three-quarter turn, if you go left, 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 you then end up going right. So if the electron goes right all the way around, and the proton goes also right, and right back to where it started from, being this idea of the quark model. It means they have the same sign of the pivot. That protons have the property that they have the same sign of the pivot, whereas antiprotons and positrons have the opposite sign of pivot. Now, if that's the case, one then has a mechanism for producing matter as opposed to antimatter. If it is the case that matter has the same property that ordinary multiplication has, you have to consider what happens if you do have pivot so you have Bohr stuff in the scalar form imposed on Bohr stuff in the scalar form. The idea is that a cancellation of field would cancel down to give you pivot, would cancel down to give you this scalar field. But the question is, if you take positive scalar field and then overlap it with negative scalar field, what do you get? You can't go to zero because that would the stuff has an energy density which is given by p squared, which is given by the square of this square root energy density. So if you try to cancel those two together, well, okay, so if you took positive and negative and stuck them on top of one another, that would go to zero, but it can't go to zero. If what it went to one or other of the signs of pivot, you'd then have an antisymmetry you'd then have a reason for the universe being matter and not antimatter. And if that could happen at thermal processes, you'd need, in order for electrons and protons to form, you'd need to have a chaotic system which was capable of producing them without their associated antiparticles. If the associated antiparticles were cancelling, then that might be a reason for having factories which produce matter near the center of some things that are very nearly but not quite black holes, as in Stephen Crowther's idea of what happens with general relativity. Now, what that would then mean is it would mean one would expect to find areas of very high mass concentration producing more mass. That mass somehow giving you a zero energy by producing more interactions which have a negative potential energy and therefore mean that energy is conserved. So you need to have that happening. But if you had concentrations of mass happening at near black holes, what you'd expect to do is find a whole bunch of places in the universe where matter was being created. Now, what would that look like? It would look like the very near black hole at the center of our galaxy, for example. If it isn't an actual black hole, but is something which is a very, very strong gravitational potential well, where there isn't a boundary between there isn't an event horizon. So I think the argument is that set of theories will work.
That's what we see, right? I mean, we see jets of new material coming out of the center of these active AGNs, active galactic nuclei.
How do we know that it's new matter?
Sorry?
How do we know that it's new matter?
We don't, but what we observe if we look out at the night sky and look at the galaxies, you see these vast emptinesses between the galaxies, because the galaxies are very big, but the spaces between them are even bigger. You see these vast emptinesses, and then occasionally you see these things with jets coming out of them, and the jets come out and it rotates and they give you these spiral forms. It looks very much as though matter's been created at the center of these galaxies, just looking at it and just being completely innocent and being a child about it and not knowing any physics whatsoever. Where is the mass? Well, it's in the galaxies. What does it look like it's coming from? It looks like it's coming from jets. So, and we find also that there's evidence that looking back in time that our galaxy's been active in the past and that Andromeda's been active in the past. These AGNs come and go.
What is that? Sorry, I'm curious. What is the evidence that? How do you see something in the past like that?
You just look further away. So you look outside for the evidence that something has been happening.
I see.
Yeah, you look. Yes. Yeah.
I mean, okay, so one option is that matter is being created, but the other option is that matter is being concentrated from elsewhere, right? Because we know that these galaxies are connected by they appear to be on filaments, right?
Yeah, that's also interesting, isn't it?
And so couldn't it just, I mean, we've had some electric universe conversations where isn't that the Z pinch at the center of the galaxy is the constriction of the galactic current filament that they're all organized on as being the reason for the emissions?
Yeah, I've seen some of these things in passing as well. I think it's very constructive to think about these things. And again, I'm not really an expert on these things. All I'm saying at the moment is it looks awfully like there are sort of active regions where galaxies where matter's been formed, and it looks awfully like there wasn't a Big Bang 3.5 billion years ago at the current state of observational data.
Mm-hmm.
So I don't know that.
Well, now Fred
stuff, but
Fred Hoyle played with this, right? With some colleagues, right, and tried very much to propose a steady state universe where these galaxies were constantly being renewed and pushing away from one another. He eventually, I believe he walked back on that, although I haven't read his writings where he walks back on this. Why? Do you have a sense for what persuaded him away from this?
No, I don't. I was going to ask you exactly the same thing. I was wondering. I think maybe he just got old and tired of the whole thing and decided.
Yeah, I wonder, because I'm reading this wonderful book by him right now, and it's before he's changed his mind, clearly, because he's just, telling these stories of hiding, people hiding their notebooks from him, and he's wandering. I forget whether he was at Oxford or Cambridge, but it's this very, very competitive environment, and he's convinced that there's this conspiracy to shut him down, and he's absolutely convinced that there's no reason for this expansion business. And I think this might have been before the CMB was discovered, and perhaps that's what got him. I don't know if he ever recanted, though. I wonder if he just sort of stopped making noise at some point. I don't know. Somebody in the comments will probably correct us on this. But it'd be interesting to
know as well what happened with that. But I think the thing is that experimentally, the thing's just an open question now. It's time people were thinking about this too, and I think you're right. I mean, it's well,
there's something very unnerving to people about things not having a beginning and an end, because our whole lives are organized around the fact that we experience the universe with a beginning and an end. Right? Our lives started at some point, and they will end at some point. And it's very, very hard, I think, for human beings to conceive of anything not having a beginning or end.
Well, it would require almost, in order to change the myth, for humans to see the myth of themselves as being eternal as well. And I think that there's a atheistic current in physics that is on one hand deeply religious, because I feel like the Big Bang is a religious idea, but there is a sense of that we come from nothing and that we become nothing. And that's also the frame of the Big Bang. And so if we could see ourselves as having more of a Vedic or an Eastern arc to our existence, then perhaps we would be more willing to see that played out in the galaxy as well. Because I know that Vedic cosmology is cyclic and eternal as opposed to birth, death.
Yes, perhaps it's because Western science is predicated on one of the religions of the book that we have this. Maybe you're right about that.
Well, one thing's for certain: the originator of the Big Bang theory was definitely a Jesuit priest. So,
look, that's
red flag. That's all I'm saying.
You can't knock somebody just because they're religious.
I'm not knocking him. I'm not knocking him. I'm just saying that that's a bias that's worth recognizing.
But it's weird because in the religious myths there is an afterlife. But the universe doesn't have an afterlife. There's no sense that the universe will die and transmute into something else. There's this really dystopian image of just the heat death of the universe where everything cools and all the galaxies are so far away from each other that you can't contact them.
Well, actually, I think that the standard model right now is that the gravitation is perfectly balancing it so that it won't expand forever. It just stays flat.
Oh, is that the case?
Yeah, I believe that's where they're at with it right now. Correct me if I'm wrong.
No, I think that's exactly right. But I do think they still have the idea of the heat death. That eventually, all the energy will be used up. But I don't think that's the case. I think new energy is being created because remember that the total energy is anyway zero. So I see us more as sort of standing on the surface of nothing at all. That what's happening is the fact that it's more that there's more phase space to a universe which has material in it and gravitation than there is to simply absolutely nothing at all is the thing that's driving the existence of the universe. It's chaos, as always. It's entropy, and this whole thing is more chaotic. It's more probable than a zero. Remember, there's different kinds of zeros. We have a zero energy, if we believe the argument that the mc squared energy is precisely balanced by a minus potential energy, gm over r squared energy. Then we're not living in energy. We're living in the dynamics of energy and the transfer of energy. And at that stage, you can, if matter is being created at the center of galaxies, there must be a balance there, because creating matter is a big bang too. It doesn't really.
It costs a lot. Yeah, it costs a lot of energy. Yeah,
exactly.
I mean, one thing that's really like stands out to me is that, especially when I was studying gravitational waves, that the pressure is very like a gravitational wave is in very much can be thought of as the inversion of a light wave. They're both transverse waves. They have inverted momentum, right? You have a tension with gravitational waves and you have a forward pressure with photons. And so again, you see this balance of energies that are equal and opposite, potentially, is kind of the way that I'm starting to look at it. Like the gravitational pressures are exactly balanced by the radiative outward pressures, and you have, maybe zero on balance, but overall there's all sorts of dynamicism occurring.
What I kind of see happening is I see the universe isn't really the way we think it is, because for light, the entire width of the universe is zero distance. To the edge of the universe and here, for those redshifted photons are at the same point in space-time. There's a connection. Now, if what's happening is matter's being created, but that's growing the number of particles in the universe, which is increasing the negative. Actually, I think it increases the negative potential energy more quickly, because it's the combinatorics that give you the very large number for gravitation. Each individual interaction is very small, but there are very many of them. So perhaps it's that. Perhaps it's the dynamics of the expansion of the universe which is driving more matter. So more matter is being created, and the universe is getting bigger, and then the edges of it are falling off. So it appears to be the same to us. Maybe something like that's happening. But I'm saying maybe here because obviously I don't know. But the thing is, I know I don't know, but I also know that the guys who are saying that there was a Big Bang also don't know equally. The evidence for that is now very, very shaky, and I think that given that it's shaky evidence, we really do need to be looking carefully at any other kinds of possibilities.
It's really interesting because there's this guy who we actually had on the show. His name is Ethan Siegel. He runs this really famous blog called Starts of the Bang.
He's also the lead science writer for Forbes magazine.
So he's a very central voice in the pop sci physics community. And I've been watching him really desperately try to minimize the data coming in from James Webb. Because his entire career to this point has been loud insistence that everything began with the bang. And
you may take that as a fact of science, yes.
and so I'm watching him do these backflips on his blog of, we can't trust these James Webb data because they're not calibrated. Then the calibrations come in and he's coming up with other alternatives for what it could be that's justifying that the calibrations, even though they do say that it's the same large redshift, are actually wrong for this and that reason, and that there's these other things that are now being kind of shoved into the model to maintain the Big Bang at all costs. Because it's a reputational failure to have insisted for so long that this is the case, to then stand around and shrug your shoulders and say, oh, well, I guess we were wrong.
I think that's an incredibly difficult thing to do for a person to work a whole career on something and then find out there's some inconvenient experiment which says it's not the case. But we as scientists have to have the humility to do that. If we find things that mean that what we're saying isn't right, then we have to just say, well, yeah, fair enough. I was wrong then, wasn't I?
Yeah.
That's a very difficult thing. Yeah, I think that's the case. So, well, we'll see what happens.
What drives you towards this work? It's esoteric. It's not inside of the academy, but it's something that clearly you have spent a life thinking very deeply about. And so what's the motivation for you?
It's big fun. It's utterly tremendous fun. Ever since, it's just, what about you guys? Come on.
Yeah, I guess just curiosity for me. Yeah, I mean, it is fun to solve problems. I love to solve problems. I love it when people tell me that there's no explanation for something besides some magical, spooky thing, and then I'm able to. I'm not saying that my explanation's right, but I'm like, well, I can at least come up with something that isn't supernatural to explain this. I feel like that's a real, I don't know, it just feels good. Like it feels like I just love solving problems. But so I guess it's driven out of curiosity because. At least when I was a kid, Anastasia, I don't know how you want to answer this, but when I was a kid, I was just combing through the library trying to figure out how the universe worked. And I was just completely bummed out by the magical explanations that I was continually handed. I was just like, even as a little kid, they just didn't make me happy. They didn't satisfy me. And so that quest to understand is powerful. I don't know. It is kind of silly, though, because it's not really rooted in anything in terms of, it's not like it's technologically grounded or anything. It's just pure curiosity for how things work.
It's curiosity, yes. It's curiosity. It's trying to work out how things work and trying to work out how other people see how it. I'm just reading. I've just had a lovely gift from one of my ex-students. He knew I wanted a copy of the third edition of Dirac. I've got a fourth edition of Dirac. But the third edition on quantum electrodynamics is very, very different to the third edition. And he's found me the third edition. He sent it to me, and I've just been reading the third edition. Where is it? It's somewhere around here. No, and the electrodynamics of Dirac third and Dirac fourth are complete. They're both wrong because of well, not wrong, but they're different. Dirac struggled really and with quantum electrodynamics. And didn't like it, and I think he was right not to like it, and tried manfully to produce a a proper theory of quantum electrodynamics that didn't have infinities in it. And it's magnificent. It's wonderful to look at that fantastic mind looking in these completely different directions to try and solve the same thing. What if it's this? What if it's that? And of course, he eventually was unsuccessful in finding something which did the charge and the mass. Okay, I've got the charge now. Still got to do the mass. But it's tremendous. It's tremendous fun to try. But it's a kind of a game as well, isn't it? Where you're trying to fit everything that we already do know about science, and we know an awful lot. You can't just come up with anything. You have to come up with something which is consistent with the parts of science that really work well, and take things forward like that. And that's a game which we three are all playing. We're all getting into that and saying, what if, and what are the problems with this? And racing those, not necessarily producing an answer to it, but okay, you have an idea, and that idea will will go a certain distance. And it can't be that because it can't be a continuous creation. You can't produce just matter because, for example, I could be completely wrong about this thing having to do with the fact. What I'm thinking is, if 1 times 1 is 1, and -1 times -1 is +1, then if you have the analogy of whatever multiplication is, but of course I'm not thinking about multiplication, I'm thinking about dynamics, which is division, and the absolute root of root energy, that minus gives you plus, and minus and plus times plus gives you plus. Then you have a mechanism for generating only plus sign material. So that's an idea. It's an idea that's based on the mathematics of a new theory. Maybe it's right, maybe it's wrong, but we have to take it to the point where we can test whether it's right or whether it's wrong, and see whether or not it fits with observation. And it's this fitting with observation thing that we have to be open to. That does mean possibly having a 50-year career and having the fun doing what Martin and I did all those years, and then finding out at the end of it all that you're just completely wrong about it, which is the likely scenario, let's face it, for every single theory that's ever been made. Most of them bite the dust on experiment. So as to why, yeah.
Oh no, go ahead, finish.
No. As to why you do that, you do it because it's magnificent. It's a magnificent puzzle. It's the biggest puzzle there is. It's a puzzle which we're all involved with. So it's not like the Times crossword where you do it and it's finished. No. There's always more to do. Anyway, sorry.
And a huge part of that is finding out what doesn't work.
Finding out what doesn't work, and also really, I think, constraining yourself too, because we talked briefly last time about the mystical and the going into the mist with mathematics, and it seems like there's a cleavage where more and more people who are doing physics are doing pure mathematics and theory.
Well, they say they're doing physics, don't they? They're pretending to do physics. But if it's just maths, it's not physics. It's not science. Science is where you come up with some predictions, then you test them against experiment. It's not just doing the maths and having a mathematics which is not testable. It's not really science.
And so if you could remake physics into something that you think is fitting for what the discipline is meant to study, what would it look like?
It would look like money being put into letting excellent people get on with trying to think of the ways stuff worked, instead of putting stuff into I think I would really be looking for experiments into much lower, many more experiments into much lower energies. More experiments into things which are accessible, which are engineerable, which are testable. So instead of having giant high energy labs, I'd have lots of much lower energy stuff doing very fine experiments on spin, on the areas. I'd have anywhere where there's a mystery, where there's a proton spin puzzle, for example, everybody jumping in and looking at that. Where there's holes and things don't work, that's where you need to look. You need to look at the stuff that doesn't fit, that fits in one theory and then is different in another theory. You need to look at those interfaces where there are problems. And that's where money should be going into. It should be going into the things that don't work, not the things that do work. and not into things which are untestable, where you don't know whether they worked or not. Certainly not that.
What is the proton spin puzzle?
We talked about it briefly last time, I think.
Yeah, I talked about that one. The proton spin puzzle is that if you do polarized proton scattering, the cross section for parallel, for the case where it looks like a Pauli exclusion principle, is 4 times bigger than for anti-parallel. Now, if you then try and look at that in terms of quarks, in terms of a bag of quarks, you've got up, down quark, and you've got so you've got 2 quarks up and 1 quark down and 1 proton, and you've got, in the case of parallel spin scattering, you've got 2 quarks up and 1 quark down and the other one. But then if you look in terms of the quarks, in the individual quarks, the cross sections don't add up. You don't get numbers like 4 times. You get a little bit of a difference between spin parallel and spin antiparallel. Whereas what you observe is something which is enormously different, far too different to fit, and that's the proton spin puzzle. Proton spin puzzle is that the proton spin puzzle is an experiment carried out in 1977, which disproved the quark model, the quark-parton model, anyway. So, and that's never been resolved. That's where you've got to look. You've got to look. So what do? They close down zero gradient synchrotron and stop looking at polarized proton scattering. What's that about? Look at the stuff that's not understood and try and, in the energy areas where that, it's much, you could have hundreds of groups working for the price of one group that's on these intermediate energy things, where you're trying to understand really relativistic quantum mechanics, making quantum mechanics work properly, looking at quantum mechanics from the point of view of the synergy with relativity, not thinking there's some sort of conflict between them. Having groups talking to one another so that you don't have tribes in physics, that it's the cross-disciplinary things are required. Having chemists talk to physicists, looking at science not as a bunch of different fields, each one of which has its own theories and its own conferences, but something which is science as a whole. Science is scientia, it's knowledge, the whole of knowledge, not little bits of it. And it's turned into little bitty fragments all over the place of people doing one string theory here, and even the string theorists don't understand each other's string theories. So there are hundreds of these theories, including mine. So that's another one of them. So where these have to be, people have to talk to one another, and in the right kind of regime. But what's stopping science is this belief system, this fact that there seems to be a mainstream and there's a consensus. That's fine when we're talking about quantum mechanics or relativity or things that are well understood, or Newton's laws. That's fine, or solid state physics. But it's not fine in cosmology and high energy physics, where this stuff doesn't work and it's not predictive. It's not fine at all. It's there that a lot of wasted effort is happening.
Do you think that we're past the era of garage laboratories for this sort of thing? Because if you look back to the to the early days of, let's say, research into electricity, the stories from Sam Gray and Francis Hauksbee are hilarious, because they're just people who they're tinkering with these contraptions and trying to figure out how electricity is working, and there's this dawn of realization that electricity might also be related to light. But I think that it was Sam Gray. He was living in a charter house where he was supported. It was basically a poor house because he didn't have a way of making any money, and so he lived in this charter house with a bunch of other, natural philosophers, and they were doing these experiments where they would see how far they could transmit electricity. And so they would have a rod on one end that they rubbed, and then they would connect various metal implements to that. And at some point in the chain, they realized that if they suspended things on silk strings, they could insulate them versus wool strings. So they got these silk strings, and there was a little boy that was involved somehow, where they would hang him in the center of this contraption and then show that you could pass current through the boy. And if you put a rod to his toes, that chaff would fly up to his face. And there's drawings of this in the proceedings of the Royal Academy, where they're showing that they can transmit electricity to you know, across feet. That they've created these crazy alignments of metal objects and this young boy, and they're like at the end,
the ultimate low energy experiment.
Yeah, like at the end you get a spark, and isn't that fabulous? And then in another paper, somebody's like, well, it's interesting because when you get the spark, you also get light, and so maybe those two are related. But it seems like we're past the era where you can build something like
unless
that.
It's a low energy experiment, right? That's the cool thing about low energy experiments is you might be able to do them cheaper.
Yeah, like can you imagine a low energy experiment that someone could do in their garage?
Oh yes. Well, not in the yeah, I can. Yeah, I can. Yes, but perhaps quite a big garage these days. And it's almost fairly decent equipment. I've got a loft up above me just here, which is kind of like 90 square meters. There's some pretty cool equipment up there as well. But it's mostly used for fixing old motor cars. So, or getting electronic devices working, which shouldn't otherwise work. That's a bit of a hobby too. Didn't work before, but yeah, no. I don't think the actual garage. I think the idea of the garage experiment is still right. We used to have at Philips, we used to have a Friday afternoon moratorium on doing your own work, and you could just you do Freitagmittag Prüfjes. You'd have a little, like a garage thing, but then with the entire resources of Philips Naturkundige Laboratorium behind you. You could do some pretty cool stuff with that, and we did. But it takes a little bit more now. But I think that we could do, not garage, but maybe local university or local industry experiments, which really did test some of these things. Lasers are not that expensive anymore. Maybe I can fix something up in the loft. I don't know, a couple of lasers, a couple of right circularly polarized. Don't need that much money, a few tens of thousands. We could perhaps do something.
No, that kind of feeds into this idea that maybe the future of science is a lot more decentralized than the system that we're looking at right now. If change necessarily has to come from the outside, it seems like they are going to be these cheaper, smaller, multiple experiments happening all over the place where people converge on some understanding that might fly in the face of something that's more monolithic and established in the past at these giant facilities.
But I think it's vulnerable to problems with funding, because if you have centralized funding that's coming from the government and the government is driving towards things that seem like they can in the long run build technologies, then there's a really straightforward rationale for investment. You put money into even something like basic biology because at the end you'll get a cancer drug out of it, or you'll figure out how to reverse aging or something. Whether or not that pans out is obviously open to discussion, but the idea of depending on smaller and smaller labs then creates a problem of who's funding it. And I think that the reason that it's not there yet is because nobody's figured that out. You have to have a stream of eccentric billionaires that are interested in funding low probability success endeavors for the sake of curiosity.
Or they're just all really cheap.
That's true, but even if it's tens of thousands of dollars, and then that's just for capital investments, then you have to be able to pay to survive while you're doing it. It's not, we're not talking about millions of dollars for each experiment, but over the course of a lifetime, it's not a small chunk of change.
You're right. You do need to have some sort of money, and this is what Quicycle was set up to try and do. The idea is to develop some patents and those, and have people, and have some technological improvements that are, some new technologies that have been developed from the new science, and then have Quicycle as a vehicle for attracting funding, and to fund basically to do the kind of thing that leads to these huge flowerings of science. We've had them before. We had them in the Renaissance. We had them at the turn of between the 19th and the 20th century, where people were funded to do the experiments of the time. Experiments in the Renaissance, of course, were such things to do with art, or the art of war in Leonardo's case, in Da Vinci's case. But what was happening is the funding was coming in to fund excellent folk to do what they could do, and the honor was in the doing. It was kind of like what happened with the space program in America, of course. That was a period of flowering in the 60s, where new things happened. We need that to be happening at a scale where people can do experiments at the mid-energy range, where people can publish and bring out things that have to do with the redshift in cosmology, for example, and possible alternatives to the Big Bang, where people are funded and are encouraged to do that kind of thing, where it doesn't get closed down, where it doesn't get pushed out to the periphery of sort of crazy people with the wrong idea, which is happening at the edges of science at the moment. Anyway, perhaps not in the center of it.
And how successful has it been successful in your view? Or
no, well, has Quicycle been successful? Have we raised millions of dollars in order to fund excellent folk to do whatever they want to do? Not yet, I'm sorry to say. But in a small way, of course, it's attracting more and more people, and it's becoming better known. So and we do have some patents to our name already. I have thought about taking the thing public and attracting and selling shares in the company, and selling shares for really quite a substantial amount. I'm thinking of, and that would then raise money to do proof of concept things. And we only need one or two of those to work, of course, and we can generate a very large amount of money, especially for such things as new energy sources. So the idea is in the longer term to do things like that with Quicycle if it's possible. And we're not the only people who are doing that. The Perimeter Institute was originally set up to do this kind of thing, to fund excellent folk. So I think that there are lots of reasons to hope. But on the other hand, there's also things to cry about.
I mean, I ask because this is something that we're really interested in as well, because obviously there's a problem in the sciences that the way that the funding is distributed is inherently bound by whatever is consensus. You know, you talk to academics and some will defend to their last breath that there's absolutely nothing wrong with the system and it's working perfectly as intended, and alternative ideas have as much play as consensus ideas. But I feel like that's not completely honest. We had a really hilarious conversation with two archaeologists on the show, and so they're both here, and we got into this question of alternative theories of archaeology, because if you've looked into it, you know that there's the consensus story arc of human development, and then there's the people that are on the Graham Hancock end of things that are like, no, Atlantis, advanced civilization before the last ice age that was wiped out. And that's a very unpopular idea, for various good reasons, because I think that Graham Hancock overrepresents his data and cherry picks. But there are people that are more careful than that, who are interested in publishing ideas about archaeology that might not line up with consensus. And these two guys, we asked them if there was issues with publishing alternative ideas, and they gave opposite answers.
At the same time.
At the same time.
One of them said yes and one of them said no at the same time.
And so to me, that speaks of some significant cognitive dissonance within the field of archaeology, which I inductively assume is the case for all fields. And so to wrap this very long-winded question into a point, is the goal of our project is to eventually be able to fund ideas, people who are working on problems that are not being worked on elsewhere. And so when I ask if Quicycle has been successful at it, I ask for very selfish reasons, because I want to understand what has worked, what hasn't, and what you think is the best approach to putting something together like this, because you have a wealth of knowledge about this.
Well, I think we should perhaps get together then, shouldn't we? Because we're doing exactly the same thing, or trying to do exactly the same thing. So has it been successful? Yes, it has, because I haven't yet told how I met Martin, of course, but since meeting Martin, other people have joined in, and some excellent folk as well. And these networks are growing, and we are thinking things that otherwise couldn't be thought about at all. So yes. it's not a currently fashionable thing to simply. At the moment, it's fashionable to put money into big science projects, and the big science projects are either at the very, very small end, it's like CERN, or at the very, very large end, like the James Webb Telescope. And I think both of them are very well. The James Webb Telescope is producing fantastic results at the moment, and I just can't wait until they find galaxies that are 200 million years or 100 million years after the Big Bang. It's going to happen. So it's this sort of thing, and I think that what happens with science is things get shaky, and then they get shakier, and eventually they get loose again, and you can have a flowering of science again after that. But I'm hopeful that money will flow into these things in the not too far distant future. But that's what we want to try and do as well. We want to try and generate, to have some means of generating enough income to be able to start getting excellent folk in to do whatever they want to do with an unlimited budget. That's what we, I think, need to do. And there's far too much in science at the moment. You have this peer review system where when I first came to Glasgow University, I put in a set of proposals which were all put down as being unfeasible and not proper science. Now, this is the sort of thing that I've just been doing at Phillips. And if I look back on the record there, a lot of those things are now being done only now, 30 years later. We should have been onto these things a long time ago. You need to really have a look at, as I say, areas where you don't understand where is not really capable, and you need to find a theory that is capable both of reproducing what has gone before in the various limits and of taking things forward in order to be able to think new thoughts. And some people can do that, and the people who can do that need to be funded. There needs to be a mechanism to fund excellence. And that's the thing that we have to work towards, finding a mechanism to fund people to do whatever they want to do. Really.
I think there's a lot of optimism there, because it seems like everybody that I meet is trying to start an institution. I mean, our friend Kurt Jaimungal over at Theories of Everything, he was on the show a couple weeks ago. He's also trying to work towards an institution that can give funding to unknown areas. We were close with the New Science, is that the name of the institution? On the East Coast, they have a little lab program set up, I believe, at MIT. Somewhere in Boston.
Or Harvard.
Or Harvard, one of those places.
I think MIT.
But it just seems like a lot of independent groups. The Cycles Foundation rates homes also. There's a lot of people who have converged at some point on this idea that if these out-of-the-box ideas are going to get attention, they need to be funded by some non-traditional means. And so I just see a lot of hope for that, because so many people are hip to that same idea.
I think the last thing that needs to be cracked in order for people to be more widely hip to that idea is fundamentally an aesthetic one, which sounds kind of silly, but I think that
it's like art. Yeah, I think you're right. Yeah, I think you're right. That was what was happening in the Renaissance. People were doing this, were funding these fantastic artists because of the honor of it. Of the fact that it was producing beautiful things, beautiful thoughts, beautiful expression, beautiful. Yeah, I really think that we've got this into the situation where everything. You were asking right at the beginning about what is physics, and I refused to answer the question and instead went for what is science, what is knowledge. I think science has this sort of very, very broad area of application, but so does art. And I think really, when we're talking about the creative, it's really a very creative thing that we're talking about, thinking about new ways of understanding the beginning of the universe, or thinking about exactly what matter is. This is an extremely creative process. It's really a form of art, isn't it?
And exactly.
It's something which is, and it has to be simple. The way that stuff works at the very basic level has to be simple, because where would the complexity possibly come from when we're talking about really elementary processes? They have to be very simple. And then the complexity flows from that simplicity. And beautiful is going to be right eventually. These are going to be very... And I think my equation I think the Dirac equation is very, very, very beautiful. But I think that the new equation, which my equation, which I hope is which I have some hope might be the thing to replace it, it's even more beautiful. It's even simpler. The Dirac equation goes d/-m equals acting on psi, where psi is some spinor thing, is equal to 0. For me, it's just d acting on psi is equal to 0. There isn't that m term sitting there as a sort of a toad sitting on the back of everything. So I think it's an even more beautiful thing. And aesthetically, in fact, there's an exhibition coming up. There's an artist who's taken some of our pictures and is showing them in an exhibition at the moment, an art exhibition in London to be shown, I think, a few months' time. I think that art and science really are different aspects of the same human thread of creativity, and the aesthetics of this are very important.
And on a deeper level, it's also that there is a reputational component of the academy that attracts people, because when you work inside of Cambridge or Harvard or MIT or Oxford, you have this weight of history behind you. It's a significance that is meaningful to people simply as a thing in and of itself. And in order to convince people to leave that behind, they have to believe that what they're leaving it for is something greater, something that is more meaningful than the old institutions. And that's the hardest thing to build, because on the very edges, when you're working with these non-consensus ideas, they haven't been hewn yet into the aesthetic that inspires a lot of confidence for people. Like, I remember mentioning to you that when I stumbled across your work, I was struck by the aesthetic of the way in which you presented it. The website is very clean. The figures are very beautiful. It's clear how much effort has been put into presenting it to the standard that is expected from a Nature paper or a Cell paper, because you come from a line of intellectual inquiry that has been trained by that aesthetic. And so you are a rarity among that world, because oftentimes you come across people's ideas and they're presented in ways that don't have that same flavor of institutional reputation. Professionalism. Yeah, because when we went to grad school, this was something that I realized where a huge portion of it was you would give these presentations and your supervisor would pick them apart until they were to the standard of what was coming out of that laboratory. And that laboratory was held to the standard of the university. And the university is held to the standard of the academic publications. And so all of it is funneled towards, this is what
quality looks like.
And that was what grad school gives you. Mm-hmm. It gives you the sense of what quality looks like, so you can go out into the world and make a presentation that rings the bell of recognition inside someone who's looking at it.
Well, thank you for the compliment on that. There has been a lot of effort going into the website over many years. Well, for some of the material over many years, and Arnie's put several years' worth of work into putting that website together as well. But yes, you're absolutely right. But I think that what's required is the rigor of science, of proper science. That's what I will put back into science, is the rigor of proper science. Not of this stuff where you make some stuff up and where you have some maths which is not really rooted in solid, testable, experimental verifiability. Now,
phenomenon.
We talked about where you look at this and say, if this is the case, then that should be the case. Is it? And then have a look, and then use that to go around the cycle of what the science used to be about and is no longer. Things that are called science now are really mathematics. And mathematics is a wonderful thing, but mathematics is not the same thing as science.
Do you think that it's possible to scrape the definition of science back from mathematics, or is it necessary to have a different word?
Well, it's interesting. I saw recently there's an essay competition which kind of goes the other way, to say that science is now almost a branch of mathematics. Do I think yes, it is. I think we have to stop. We have to distinguish between things which which are at least calculable, which have the possibility of verification from things which aren't. And well, Faraday had a name for theories, and Michael Faraday was a magnificent example of a flowering of science from a non-scientist. And he called all theories speculations, and that is exactly what they are.
Yes,
they are speculations. And you have a speculation about something, and you think maybe it works like this, and then, well, then you work out what the consequences of that are, and if the consequences of that don't accord with reality, then really you just not got it. It's just wrong. But it has to fit with what's observable and with what you see. It has to be consistent with that. I know we had this discussion about things that couldn't be testable, where you couldn't set up an experiment, you can't set up a big bang. Well, maybe you can. Maybe you can't set up a big bang, but maybe you can set up a matter creation facility of the kind that I just said. Now that's something which might be testable. What you do is you try and create this stuff at very, very large sizes and see if you can put the right spin, and I mean spin here in both in the sense of actual quantum spin, in to create matter as opposed to antimatter. That experiment is divisible and should be done.
Yeah, the Redshift stuff seems like it would be, I would love to see somebody funded to try to produce redshifts that were non-Doppler, non-gravitational, different ways of producing redshifts on Earth in a laboratory that could potentially contribute to our understanding of cosmic redshifts as well. Exactly
that. I've said, well, maybe it's like going in the opposite direction. Well, fine, test it. Have a look at see if there is a shift if you set that thing up. Okay, so then Williamson's conjecture, Williamson's speculation about that was simply wrong. Simple. So do the experiment. Now that experiment is it's not very cheap, but it's not expensive as on the scale of CERN. It's quite a doable experiment. We should be having more experiments like that, and less that are the Me Too experiments. I'm quite amused. I've had about 6 citations today to one of my papers, and all these papers, what these papers are doing is they're essentially saying, we've just done the same thing that Van Houten and Baineker and Williamson and co. did 30 years ago in a new material. And then they got a paper about that. Now, of course you're going to get that effect. So what? The effort could very much better be put into things which are new and which take things forward. There's far too much stuff which is, it's perfectly good publication. I see why people are trying to get publications. It's what you need to get promotions. It's what you need to get your tenure. It's really a waste of time.
Yeah, because you need something with positive results in order to apply for funding. That's what's strange. So you can't just spend all of your time playing around, because you have to deliver, we're making progress towards this, that, or the other thing. You can't just have I just need money to play around in my lab for the next 10 years, which is a bit tragic in the main funding paradigm.
But that's what it should be. It should be, give me money because, why? Because my track record is we've done some interesting things, or because you'd have a group of people, 60-year-olds down to 20-year-olds coming in, and if the 60-year-olds and the 40-year-olds have reputation, let them do what they want to do. Set them free. Give them money to do, or to fund excellent people coming up to do whatever they want to do. This is what should be happening. Whereas what we get something which is a bit more corporate. People are looking for, I think what it ends up with is you end up with a high level of mediocrity. You're not doing excellent. It's not terrible stuff. It's not absolute nonsense, but it's cutting out both the dross and the speculative and the potentially excellent. And there needs to be a means of funding the potentially groundbreaking, and there isn't at the moment.
This is something go ahead.
Well, except for if you happen to be a prince with your own fortune and want to do this kind of thing like De Broglie was.
I think we will see more of that. I really do. I don't know about princes, but I think that the independent funding structure is what's going to save this mess.
I think that there's enough billionaires in the world that are interested in esoteric scientific questions that the only real challenge is figuring out how to get access to said billionaires.
How to connect them to the people who are doing the experiments.
Yeah, and I think that one of the most important questions for that is a set of judgment criteria for what counts as work that is worth funding.
Yeah, that's right. And, okay. I think that what that is that stuff that I think it's going to have to be proof by engineering, trying to go for things that are, well, what are we missing? We're missing room temperature superconductors. How do you do that? What are the things you need to, that would be a very useful thing. What about not a superconductor, but a perfect conductor, something which has zero resistance, but doesn't exhibit a Meissner effect? That's another useful thing. How about going for new sources of energy, going for tests of gravity, for methods of one of the big problems for space travel is that humans get turned to jelly if you try and accelerate them too much. So can we deal with that kind of thing? What are the sorts of things that we need to do in order to make the next progress? What about the next kind of electronics? We've got semiconductor stuff here. What's the next electronics going to look like? Well, I can tell you what it's going to look like eventually. It's going to be stuff which is metal insulator electronics. Is anybody doing any real research on metal insulator electronics? Well, not as much as they should be doing. So why does it have to be metal? Because you need to get the electrons small enough. You need to get small electrons if you're going to make things super fast, because they need to be close together because of the limitations of the speed of light. And now, those things are the things that we should be funding, things which actually make stuff work, which cut new ground. And we're not, because they're thought to be too risky, or, well, yeah, too blue sky. I don't know what it is. I don't know why that sort of thing doesn't get funded.
I mean, do you think that you could take out basic research findings from that? Like, obviously, you're not going to have a technological implication for studying redshift in a laboratory immediately, unless you can devise a scheme for which that will play into some technological paradigm in parallel, right?
I think if you're looking at stopping light, for example, and seeing that as a possible thing for redshift, then yes, that can very much feed into technological things. So, and I think also to say that it's not going to feed into technological things is exactly something that you don't know. You don't know what kind of technology. You cannot imagine that doing research on radiation is going to lead to a nuclear bomb now, can you? Before it's actually appeared. So this is a very unlikely scenario. No, knowledge for its own sake is what you need to pursue.
This is fundamentally a very reasonable position. And so when you talk to colleagues that are still inside the academy and perhaps are working along more conventional lines, do you run into people that disagree with this?
No. The problem is that when you try and get funding to do that, then what happens is some anonymous referee somewhere thinks that whatever they're doing in that area, so it has to be in an area. So what area is it going to be in? It's going to be in, it's going to be in quantum transport in semiconductors. So the whole thing is quantum transport in semiconductors. And you come along and say, well, actually, we don't want to do semiconductors. We should really be doing metals and insulators. Then they say, well, that's not really supposed to be funded in quantum transport and semiconductors, now is it? So why don't you go to the quantum transport and metal insulator systems people who don't exist? so of course they don't exist. You're doing something new. There isn't a place to apply for the funding for that sort of thing to get that within a university context. Now, okay, where could you get it? Well, you could get it in a very, very large industry context who want to take the next step in super fast electronics. And that would be the place that it would be appropriate to do such a thing. And that's where it's eventually going to happen.
Do you think that it's already happening?
Do I think it's already happening? I think if it's not already happening, it ought to be. And I very much hope the United States or Denmark or Western European countries are doing this sort of thing, because they damn well ought to be.
I mean, I've already seen this play out inside of the academy itself. I got all of my funding for my graduate work from the Department of Energy and the Department of Defense by selling them the dream that what I was working on would somehow tangentially be useful to them, and of course had to paint the picture of maybe the potential for how that could work out. But in all honesty, I was asking very basic science questions with the research I was doing. It's just that I had to frame it in a way to these funding organizations so that it seemed attractive to them in their own interests. But in reality, the questions were actually very basic that we were asking that didn't really matter to them necessarily. It's just that the findings could somehow potentially play into what they're interested in. So it's almost like this alignment issue of how to make your ideas fit into some fundable umbrella. And I think that some of the more successful academic labs are able to balance that and play that charade a bit.
I think that's right. I think if you've got enough money, and you can divert some of it to the Friday afternoon stuff where you're actually doing blue skies research. But it shouldn't be like that. What it should be is, hey, we've got a research facility here which can do all these things. There's a bunch of excellent people there. Maybe if we just put money in 1 day a week to let them do whatever they want and get together, and maybe something will come out of that. So let's stick a pile of money in to do that. But it doesn't work like that. It has to be a specific project, unfortunately, for us in Britain anyway. I think the same for you, and maybe it's better in the United States or better elsewhere, but for us in Britain, it's like that.
Yeah, I just think it comes down to the way that people are trained in terms of this single-minded focus. Like, we're going to ask for money for this, and we're just going to work on that and work on that. But it takes a very unique and forward-thinking investigator to say, oh, I'm just going to put some of this money aside or this time aside to work on this project. Like, when I first showed up in my lab, I realized much later that I had a really, really unique grad school experience and that most labs don't work like this. But my boss literally told me when I showed up, I was like, well, what do you want me to work on? He was like, just take the next year and just play with the system and see if you can find anything interesting happening. And I was like, what? Are you serious? That's crazy. And he was like, look, man, the average Nature paper costs $500,000 to pull off. So, we've secured funding. So now spend some of that money and just look for something interesting. And I don't think that most laboratories have that luxury. Like, they don't have that. They're not unburdened enough to say we're going to take time to just mess around. It's almost anathema to the single-minded focus of, okay, we have to get this result now. And I think that could come down to just people making that choice, to just break off some of their funding for play. I think it can happen, and I think it is happening, but it could be more widespread, I think, in these independent institutions.
You have to try and identify it takes a special kind of person as well to do things which are going to be groundbreaking. That's a special talent. You don't get it taught it. You can't be taught to be. It's something which people have in very, very, very variable amounts. We're not talking about people are twice as likely to do something or 4 times. It's 10 times, 100, 1,000 times. So if you can identify those people and then give them play and then give them resources, then you can fly. Mm-hmm. Then you can really fly forwards.
I mean, I think that there's a lot of reason to be optimistic for the future. And I think that organizations like the Quantum Bicycle Society and many of the other people that we've talked to are all converging on the same point. And that's, I think, in history, what has proved effective.
I feel the same way. I think that we're close to a paradigm shift in the way these things go and getting back to proper science. I hope that's the case anyway. That's what we're working towards anyway ourselves now in our own small way. And you're right. I mean, there are other groups as well. The Models of Particles group. There are groups that have existed for a long time trying to do this thing. ANPA, Alternative Natural Philosophy Association, has some good people working there as well. Peter Kaufman, Garnet Ord, who are also associated with Quicycle. I think the fact that we can have this kind of communication. I mean, where are you guys actually based? West Coast United States, is that right?
Yeah, we're in the middle of nowhere. We're exactly in the middle of nowhere. We're right on the border of California and Oregon. So.
Oh yeah, that's a great place to be. Good, yeah. I never quite got that far north in California. Great place. Okay, but the fact that that and Scotland, and I have a collaboration with the guy. My collaborations are now with people in Australia and in the west coast of the United States and all over the world. The fact that these groups can come together and are beginning to form networks between them, I think, is extremely important as well.
Yeah, I'm excited for the future.
Yeah. Do you have any? We've been talking for almost 3 hours at this point. Do you want to put a closing ribbon on it?
Well, I think that what is needed in terms of this is really being honest with oneself, having a look at what we know, the whole of what we know, not little bits of it, and then trying to come to a picture which brings all of those things together. Because I think the very large and the very small, although they seem very far apart, are both very, very important for understanding the fundamental nature of reality, as the discussion has shown over the last few hours as well, that we've been switching between the very, very large, very small particle and the very large, and the effect each of those has on them. We have to break down the barriers between the different areas of science. We have to understand each other's areas and see what effect and how we can integrate that with our understanding of what we're trying to do, each of us, and come together in terms of coming to some sort of consensus on this, and really call out the things in each other's thinking that don't make sense. We have to call out the things that don't. If they don't make sense, you have to go, wow, this really doesn't make sense. Isn't that great? Because that means that just here, right at this point where we don't understand what's going on, we have something to learn. And it's that we've got to concentrate on. Why is this clash happening? How is it that stuff has been, the matter has been created? What's that cosmologically? How does that happen intensively? How is that? What kind of system does one need to make that happen? How could it be that the universe could come into existence and follow the laws of physics? Wouldn't that be nice if we could work out how? So it's in these places where we don't get stuff, where it's a mystery, that we really need to acknowledge that it's a mystery and that we don't know that there was a Big Bang. We can't do the stuff in experiment, that these are speculations. We have to have the humility to play with our speculations and to enjoy the speculations, and then also enjoy the fact that some speculations can be excluded on the grounds of experiment.
I love what you just said about the discoveries originating and recognizing that what you thought was going to happen isn't what's happening. And I forgot to even tie the bow on my story about playing in the lab in grad school. How do you know that you've found something interesting? Well, the things that are interesting are the things that are not what you expected to find. And so,
that's right.
Yeah, my boss would always say to me, well, it doesn't matter what this experiment says. If it's what we expected, great. If not, then that's even more exciting. And we'll have to rethink our theory from the beginning, and that could be even more groundbreaking. And it was just wild because no one ever sits you down when you go to grad school and says, here's how you make a discovery, right? But in reality, that's a really important thing to teach kids, is that the discoveries come out of recognizing that things aren't happening how you thought they would. And that's cool. That the fact that your experiment didn't work is awesome, because now you can learn something.
Null result. Absolutely great. Yes, because why didn't we find any glue balls? Because the theory is no good for explaining this kind of thing. It's just no happening. It's no there.
Yeah.
Well put. Well put.
There is one thing that I wanted to say, and I'm glad I've remembered it. That is, I was very confused about them. I come from a place in Scotland which is the smallest county in Great Britain. It's called Clackmannanshire. And we have mottos for counties, and the motto for Clackmannanshire is "Look about ye," which means look around you. And I thought, that's a stupid motto. I mean, look around you, so what? But actually, do you know what? That is the proper thing to do. It's really to look around, to look at everything, to look at all the mysteries that are playing out here, to wonder at those mysteries, and then to sit down there and take a walk in the countryside or something and think about them and think about how they fit in with everything else. And can you bring them all together And sometimes the most disparate things come together to give you an insight into how stuff works, into how things work really at the elementary level. And that's the game which I think at least the three of us are playing, which has been played for a long time. We're playing this game that's been played for 2,500 years, or at least 500 years since science started. And together we're telling a story which grows, and occasionally it grows off in some strange direction, which is not quite right, and then boom, click, comes back, and then we go somewhere else, which is better founded. That's the way that science is working. I think we're at a point where the whole structure here in some of these things that have been a wee bit crazy is beginning to teeter. And it needs to come back to the core, to the proper scientific method of try and understand experiment with theory, then look at the theory, say what the theory's predicting, devise experiments to test those areas which are mysterious, and if it doesn't work, then modify the theory or throw it away and make up a completely new theory which does work. So that process is a long process. We're very lucky to sit in the 21st century. We have all sorts of wonderful things and wonderful people who have thought a lot of things which we've learned an awful lot from. But I think it's time there's a big paradigm shift in science. I think that paradigm shift has to come. It is happening. It's beginning to happen. And I'm really happy about the younger generation at the moment, because they seem to have got that curiosity back, which seemed to be missing for a long time. So I'm just delighted to see that happening.
Yeah, it's fascinating that all of our cognitive biases in some sense can be boiled down to target fixation of some sort, where you're just really chasing what you expect to happen, and you keep chasing it, and you forget that like you're being swarmed from all sides by other interactions.
This is a funny story. The other day, Shyla was looking for something, and like we have this, we make pizza, and we have this grabber that like holds the pizza pan, and he goes looking for it, and he comes back and he's like, I can't find it. And I go, and it's, lying in plain sight. And I was like, how do you look for stuff? And he's like, well, I look where it's supposed to be. And I'm like, oh, that's the secret. Because when I look for something, I look for all the places where I don't expect it to be, because it's not where it's supposed to be.
You see, you were in possession of better information because you knew that Charlotte had already looked for it.
Yeah, that's true. But But it's a standard way of searching. When I was younger, my mom would always be able to find stuff, and I never knew, she seemed to have this encyclopedic knowledge of the state of all objects inside the house. And it has taken me 20 years to develop the same sense, and I've figured out the key is that she never would look for it where it was supposed to be.
I mean, I really tried to study this a bit, and there is some sex differences in this. So it seems like this problem afflicts men more than women, but it's something they really are working against, particularly in the military special operation forces, is how to get people not to be so, especially men who are in these units, to not become so fixated on what they expect to be occurring that they don't get swarmed from the sides or from the rear or something like that, because it's a huge cognitive bias in men in particular. You just you know what you expect and you go for it. Yeah. But anyways, this is absolutely. Yeah.
I mean, this has been it's been a real joy to get your perspective on the world and to understand the questions that drive you, and to understand what goes into solving these sorts of puzzles. And so I'm very grateful that you've taken the time to give us all of this.
Well, I'm very grateful that you've given us the platform to expand a little bit on what we're doing, and that you'll be talking to Arnie as well, and perhaps some more of us at some point in the future. So Indeed. Thank you very much as well. I look forward to some interactions as well. Outside the field of these podcasts as well. So I'll try and keep you in the circuit as well as to what we're doing.